before we go anywhere tonight, you can let the day become smaller. There is nothing you need to solve, nothing you need to remember, nothing waiting inside these next few hours that requires you to stay awake. You can listen for as long as you like. And when the words begin to blur at their edges, you can let them. You do not have to follow every sentence. You do not have to hold every fact. You do not have to remember which spacecraft flew on which morning, or which astronaut looked through which window, or which machine was carried into the darkness above Earth. Tonight, forgetting is allowed. In fact, forgetting may be useful, because we are going somewhere that was built from checklists, thousands of them, a world in which almost everything had a name, every switch, every valve, every procedure, every sound that was expected, and many sounds that were not. But none of those things need to become your responsibility. You are not sitting inside the cockpit. You are not watching the clock. You are not waiting for a launch window. You are simply here, listening, breathing, perhaps lying beneath a blanket, perhaps noticing that the room has become quieter than it was a few minutes ago, perhaps noticing nothing at all. That is fine too. The body does not need instructions for everything. It already knows how to become heavy. It already knows how to loosen its grip on the day. It already knows how to cross that strange, invisible border between being awake and almost being asleep. So let it. There is nowhere else you need to be. For a while, we will move slowly, very slowly. We will travel through 30 years of human spaceflight, through 135 journeys away from Earth. Some lasted only days. Some carried satellites. Some carried laboratories. Some carried pieces of a space station so large that no single rocket could have launched it whole. Some went into orbit to repair something. Some went to retrieve something. Some went simply because there were questions that could be answered more clearly in weightlessness. And two never came home. We will not hurry past those. We will not turn them into spectacle. We will simply remember them when their place in the story arrives. But that is still far ahead. For now, there is only the room around you, the surface beneath you, the quiet rhythm of breathing, and somewhere very far away, or perhaps only far away in memory, there is a coastline in Florida. It is still dark. The Atlantic Ocean is nearby. The air is humid. The launch pad stands beneath floodlights, and something enormous is waiting. But not yet. We have time. You can let your shoulders settle. You can unclench your jaw. You can allow your hands to rest wherever they have decided to rest. There is no correct position. No countdown has begun. No one is asking anything from you. For the people we will meet tonight, sleep was sometimes difficult. Spaceflight has schedules, experiments, meals, communications, exercise, maintenance. Orbital mechanics does not particularly care whether a human being would prefer another 20 minutes under a blanket. But you are not in orbit. Gravity is holding you gently where you are. You do not need straps to keep yourself from floating away. You do not need to attach a sleeping bag to a wall. You do not need to remember where you placed a pencil, only to discover that the pencil has quietly migrated behind your head. Tonight, gravity can do the housekeeping. Let it hold you. Let the room become ordinary. Let ordinary become comfortable. And let comfortable become distant. There is a peculiar thing about falling asleep. You rarely witness the exact moment when it happens. You can notice yourself becoming tired. You can notice thoughts becoming less orderly. You can notice one idea turning into another without asking permission. But the border itself is difficult to observe. The moment you successfully notice that you have fallen asleep, you are awake enough to notice it. Spaceflight has a similar problem. There are boundaries everywhere, the edge of the atmosphere, the beginning of orbit, the moment a vehicle stops behaving like an aircraft and begins behaving like a spacecraft. Yet many of those boundaries are not lines that nature has drawn. They are changes in behavior, changes in speed, changes in pressure, changes in what the machine must become. And that is where we are going tonight. Not toward a single flight, not toward a single astronaut, not even toward a single spacecraft. Calm down, relax, settle in, subscribe. We're following this all the way to the edge. We are going to follow a machine that spent 30 years changing its job, again and again and again, without changing the shape that most people remember. A white spacecraft, black beneath its wings, a broad delta shape, a vertical tail, windows at the front, a cargo bay along its back. At launch, it stood beside an enormous orange external tank and two white solid rocket boosters. In orbit, it became something else, a ship without the ship beneath it, a winged machine moving around Earth. And when it came home, it became something else again, a glider, a spacecraft with no second attempt at landing, one approach, one runway, one chance to place an extraordinarily complicated machine back on Earth. But we are getting ahead of ourselves, so breathe slowly. There is no need to picture every detail. The images can come and go. The words can become softer. The facts can drift past without being collected. You are allowed to miss things. You are allowed to sleep through entire missions. The spacecraft will continue without you. It has already flown. Every launch we will visit tonight has already happened. Every landing is already written into history. There is nothing you can change, nothing you need to prevent, nothing you need to anticipate. The story is complete. And perhaps that makes it a good story for sleep. We already know that the final shuttle landed. We already know that the runway eventually became quiet. We already know that the orbiters now rest on Earth. So tonight, we can move through the story without chasing the future. We can simply watch the past unfold, slowly, one mission at a time, one change at a time, one orbit at a time. And if you fall asleep before the first launch, that is perfectly all right. If you remain awake for 10 missions, that is perfectly all right. If you wake much later and discover that the spacecraft has somehow travelled through decades while you were gone, that may be the most appropriate way to experience it. Because the Space Shuttle program itself can feel strange when viewed from a distance. It begins in one world and ends in another. At the beginning, personal computers are rare. The internet, as most people know it, does not exist. The Soviet Union still exists. No human being has lived continuously aboard the International Space Station. The Hubble Space Telescope has not yet been launched. By the end, all of those things have changed. The spacecraft has not merely crossed space, it has crossed time, and throughout those decades, the silhouette remains familiar. That is the strange part. Imagine a spacecraft standing on a launch pad before sunrise. Do not imagine the noise yet. Do not imagine the fire, just the shape. A winged vehicle attached to a tank and two enormous boosters. It looks complete, finished, as though someone designed a spacecraft, built it, and then spent 30 years flying the same thing over and over. But that is not what happened. On one flight, the cargo bay carried a satellite. On another, a laboratory. On another, a telescope. On another, equipment meant to catch a satellite that had already gone wrong. On another, a docking system for meeting a Russian space station. On another, pieces of a new space station that did not yet fully exist. Sometimes the crew released machines into orbit. Sometimes they brought machines home. Sometimes astronauts left the cabin and worked outside. Sometimes the most important work happened inside a pressurized laboratory hidden in the cargo bay. Sometimes the shuttle became an observatory. Sometimes it became a repair shop. Sometimes it became a ferry. Sometimes it became a crane. The outside remained recognizable. The purpose did not. And so, before we begin with the first flight, there is one small question worth carrying with us. How did the same spacecraft idea keep becoming a completely different machine, without ever changing its basic shape? That is the question we will carry through all 135 missions. Not simply, what happened? The mission records can tell us that. Launch dates, crew names, payloads, landing sites, orbital durations. Those details matter, and we will move through them, but beneath those details is something quieter. A machine designed before its own future existed. When Columbia first rose from Florida in 1981, there was no International Space Station waiting for it. There was no Hubble Space Telescope waiting to be repaired. There was no shuttle and Mir partnership waiting for a docking vehicle. Many of the jobs that would later define the shuttle program had not happened yet. Some had not even been fully imagined in the form they would eventually take, and yet the vehicle had to survive long enough to meet them. That is unusual. Machines are normally built for jobs. The shuttle was built around a collection of abilities: a large cargo bay, a robotic arm on many missions, an airlock, a crew cabin, orbital maneuvering engines, wings for returning to a runway, the ability to carry people and cargo together, and from those abilities, new jobs emerged. The question is not whether the shuttle changed. It did. Hardware changed. Procedures changed. The orbiters differed from one another. Safety systems evolved. Payloads transformed the meaning of individual flights. The question is how much change could be hidden inside one familiar outline. How did the same spacecraft idea keep becoming a completely different machine without ever changing its basic shape? We will begin with a shuttle that does not yet know how to be any of those things. It has never carried a satellite into orbit. It has never repaired a telescope. It has never docked with a space station. It has never helped assemble a permanent human outpost above Earth. At the beginning, it has a simpler task. It must prove that it can leave, and then, somehow, come back. So let the room around you grow quieter. Let the coastline of Florida appear somewhere beyond the darkness. Let the year become 1981. A spacecraft is waiting on launch pad 39A. Its name is Columbia. 2 astronauts are inside, and no human being has ever flown this kind of spacecraft before. The familiar shape is still learning what it can become. Let us begin. The first mission was called Space Transportation System 1. It launched on April 12th, 1981. The date carried an echo. Exactly 20 years earlier, Yuri Gagarin had become the first human being to orbit Earth. Now, on another April 12th, John Young and Robert Crippen were preparing to fly a spacecraft that looked unlike the capsules that had carried people into orbit before. Columbia had wings, it had a cargo bay, it would launch vertically, it would orbit Earth, and then it would return through the atmosphere and land on a runway. That sequence sounds familiar now because the shuttle eventually made it familiar, but on the first morning, it had never been done by this machine. There had been no uncrewed orbital test flight of the complete Space Shuttle system. Columbia's first journey into orbit carried people. John Young had already travelled to the Moon. He had walked on it during Apollo 16. Robert Crippen had never flown in space. One veteran, one first-time astronaut, and around them, a spacecraft that was itself a first-time traveller. The mission lasted a little more than 2 days. Its purpose was not to begin the long catalogue of satellite deployments and laboratories that would come later. Its purpose was more fundamental. Fly the vehicle, test its systems, bring it back. Columbia completed 37 orbits of Earth. Then it returned. It landed at Edwards Air Force Base in California. The first shuttle mission had done something that would soon appear routine in photographs. A spacecraft had come home on wings. But routine is a word that history applies backward. Nothing about the first flight felt routine to the machine. The thermal protection system had to survive re-entry. The flight controls had to work across radically different environments. The orbiter had to transition from a spacecraft moving through near vacuum to a glider descending through thickening air. The landing gear could not be tested in the usual way during approach. Once lowered, it remained lowered, and the engines that had helped send Columbia toward orbit were not available for a second landing attempt. The shuttle returned as a glider, a very heavy one. This is the first answer to our question. How did the same spacecraft idea keep becoming a completely different machine, without ever changing its basic shape? Because even on its first mission, it was already more than one machine. During launch, it was part of a stacked rocket system. In orbit, it was a spacecraft. During re-entry, it was a blunt body protected by thousands of thermal protection tiles. During final approach, it was an unpowered aircraft. The transformation was present from the beginning. The familiar shape was still learning what it could become. The second flight came in November of 1981. Again, Columbia. Again, 2 astronauts, Joe Engle and Richard Truly, Space Transportation System. 2 was planned to last longer than it did. A problem with one of Columbia's fuel cells shortened the mission, but something historically important had already happened the moment Columbia launched. The orbiter had gone to space before, and now it was going again. Reuse was no longer a promise sitting on a drawing board. A spacecraft that had returned from orbit was returning to orbit. The second mission also carried the first version of a scientific payload known as the Shuttle Imaging Radar. From orbit, radar observations could reveal features of Earth's surface in ways ordinary visible light could not. Already, the empty idea of a cargo bay was becoming specific. The shuttle could carry instruments. It could turn orbit into a temporary platform for observing Earth. Then came Space Transportation System 3. Columbia again, March of 1982. Jack Loosmer and Gordon Fullerton. This time, the mission lasted more than 8 days. The shuttle was stretching its legs. If a spacecraft can be said to have legs, which, in this case, would be slightly confusing because the landing gear was usually hidden. The mission tested the orbiter for longer periods in space. It carried scientific experiments, and its landing plans changed because weather affected the intended landing site. Columbia eventually landed at White Sands Space Harbor in New Mexico. That made the mission unusual. Most people remember shuttle landings on the long runway in Florida, or across the dry lake bed at Edwards in California. But for one mission, the white gypsum landscape of New Mexico became the place where an orbital spacecraft returned to Earth. The shuttle program was still learning where its boundaries were. Then came Space Transportation System 4, June of 1982, Columbia again, Thomas Mattingly and Henry Hartsfield, the 4th orbital flight test, and the last mission in the initial test phase. After 4 flights, the experimental chapter was officially giving way to something else. Operational flight. That phrase sounds almost sleepy. Operational, a word for schedules and procedures. A word suggesting that the extraordinary has been filed into a cabinet. But the next missions would reveal something important. There was no single thing called an ordinary shuttle mission. The vehicle had passed its first examination. Now people began placing jobs inside it. Space Transportation System 5 launched in November of 1982. For the first time, 4 astronauts traveled aboard the shuttle. And for the first time, the shuttle deployed commercial communications satellites. The cargo bay was no longer merely a place for test equipment. It was becoming a delivery space. The shuttle could carry a machine into orbit, open its doors, release that machine, and continue flying. The mission was also supposed to include the first shuttle spacewalk, but problems with the spacesuits prevented it. That detail matters, because the shuttle's future would depend heavily on astronauts working outside, repairing, building, handling objects that were never meant to fit through a cabin door, but that future had to wait. The first 5 missions all belonged to Columbia. Then, in April of 1983, a new orbiter reached space, Challenger, Space Transportation System 6. The first flight of Challenger. The mission deployed the first tracking and data relay satellite, and astronauts Story Musgrave and Donald Peterson performed the first spacewalk of the shuttle program. The cargo bay doors were open, 2 human beings moved outside, and another possibility became real. The shuttle did not merely carry cargo, it could carry a workplace into orbit. The familiar shape was still learning what it could become. Space Transportation System 7 followed in June of 1983, Challenger again. The crew included Sally Ride. She became the first American woman to travel into space. The mission deployed 2 communication satellites. It also used the shuttle's robotic arm to release and later retrieve a free-flying scientific platform. That sequence contained a quiet preview of the future. Release something, move away from it, find it again, reach toward it with a mechanical arm, bring it back. The shuttle was beginning to interact with objects in orbit rather than simply passing through orbit itself. Space Transportation System 8 launched in August of 1983. Challenger. The crew included Guyon Bluford. the first African American to travel into space. The mission launched at night, and it landed at night. Another boundary crossed, another set of procedures tested, another version of the same machine. Then came Space Transportation System 9, Columbia returned, November of 1983. And inside its cargo bay was something that changed the character of the shuttle, Space Lab, developed by the European Space Agency. Space Lab allowed scientists and astronauts to conduct research in a laboratory carried aboard the shuttle. The cargo bay had become a room for science, not metaphorically, physically. A pressurized laboratory module traveled behind the crew cabin. Astronauts could move into it and conduct experiments in orbit. The shuttle was becoming a temporary space station, not permanent, not independent, but for the duration of a mission, a laboratory above Earth. This is what the first 9 flights reveal. The progression is easy to miss when mission names become a sequence. 1, 2, 3, 4, 5, 6, 7, 8, 9. But beneath the numbers, the machine was accumulating verbs: launch, orbit, return, fly again, observe, deploy, walk outside, release, retrieve, experiment. Each mission added another action, and the central question becomes slightly sharper. How did the same spacecraft idea keep becoming a completely different machine without ever changing its basic shape? Because the shape was not the mission. The shape was a container for possibilities, and now those possibilities were beginning to multiply. The first 4 flights asked whether the shuttle itself could work. The next 5 began asking what work the shuttle could do. Those are not the same question. And once that distinction appeared, the program began to accelerate. More orbiters would arrive, more crews, more satellites, more experiments, more complicated encounters with machines already circling Earth. Soon, astronauts would attempt something that sounded almost like a scene invented for a film. They would fly toward a satellite that had not reached its intended orbit. They would meet it in space. They would bring it inside the shuttle, and they would try to fix it. The spacecraft was about to discover a new job. The familiar shape was still learning what it could become. Let us go find it. Before the shuttle could become a repair shop in orbit, it first had to learn how to reach beyond itself. That sounds simple. It was not. A spacecraft can carry something into orbit. It can open its cargo bay doors. It can release a satellite. And then, in the simplest version of the story, the satellite drifts away and begins its own life. That was already happening. But what if the object was not leaving? What if the object was already there? What if the shuttle had to find it, approach it, match its motion, move close enough for a human being to reach it, and then, somehow, take control of it? This was a different kind of flight. The shuttle would no longer be merely a vehicle traveling through space. It would have to become a vehicle that could work inside space. The distinction is subtle, but it changes almost everything. Imagine 2 objects circling Earth. From the ground, they may both appear to be moving unimaginably fast, and they are. But speed alone does not tell you whether they can meet. 2 spacecraft can travel around the same planet and remain hopelessly separated. They can occupy different orbital planes, different altitudes, different positions along their paths. One can pass above a location minutes before the other arrives, and in orbit, minutes can become thousands of kilometers. You cannot simply point the nose of a spacecraft toward another object and fly straight at it. Orbit does not behave like an empty road. If you change your speed, you change your path. If you change your path, you change where you will be later. Sometimes, slowing down can eventually make you catch something ahead of you. Sometimes, speeding up can place you in a higher orbit that takes longer to complete. The intuitive rules of movement become rearranged, and so the hidden question inside the shuttle program was becoming clearer. The obvious question was whether the shuttle could carry things. It could. The more interesting question was whether it could interact with things that were already free. Could it become precise enough to work with the orbital environment rather than merely survive inside it? Because if it could, the cargo bay would become something much more unusual. It could become a destination, a place where objects from space might arrive. The familiar shape was still learning what it could become. The 10th shuttle mission was Space Transportation System 41B. It launched in February of 1984. Challenger returned to orbit. The crew consisted of Vance Brand, Robert Gibson, Bruce McCandless, Ronald McNair, and Robert Stewart. The mission carried 2 communications satellites for deployment, but the image that came to define the flight did not show a satellite. It showed a person, alone, floating above Earth. No cable connected him to the shuttle. No tether led back to the cargo bay. Bruce McCandless was flying freely. He wore a device called the Manned Maneuvering Unit. It was a nitrogen-propelled backpack designed to allow an astronaut to move independently outside the spacecraft. The idea was not entirely new. Astronauts had moved outside spacecraft before. They had used handrails, tethers, mechanical aids. During the Gemini program, astronauts had discovered how physically difficult working outside a spacecraft could be. Moving in weightlessness was not the same as moving without effort. A body still had mass. Tools still had mass. Every push created another motion. Every attempt to stop required control. The Manned Maneuvering Unit offered something different. It allowed an astronaut to fly untethered. During Space Transportation System 41B, Bruce McCandless moved away from Challenger. Later, Robert Stewart also tested the device. The photographs are among the most recognizable images of the entire shuttle era. An astronaut, a white suit, a small propulsion unit, the blue curve of Earth below, and nothing visible between the human being and the spacecraft. But the photograph can make the moment seem simpler than it was. The important thing was not that a person could float freely. Astronauts already floated. The important thing was controlled movement. The astronaut could translate, rotate, approach, retreat, stop. The backpack turned the astronaut into a very small spacecraft, and that mattered because the shuttle was preparing for a new kind of work. If a satellite needed attention, the orbiter might not always be able to place its entire cargo bay exactly beside the required point. A human being might have to cross the remaining distance. The Manned Maneuvering Unit was one possible bridge. The mission also tested another device called the Manipulator Foot Restraint. An astronaut could attach to the end of the shuttle's robotic arm and use it as a movable work platform. One system allowed a person to fly freely. The other allowed a person to be positioned by a mechanical arm. 2 different answers to the same emerging problem. How do you place human hands exactly where they are needed in a place with no floor? The question sounds almost domestic. Move this person over there, but in orbit. Over there is moving around Earth. So are you, so is the spacecraft, and every object you touch can begin moving too. The hidden question was becoming sharper. How did the same spacecraft idea keep becoming a completely different machine, without ever changing its basic shape? By learning to control the space immediately around it. Not only the space inside the cabin, not only the cargo bay, the invisible volume beyond the open doors, the area an astronaut could reach, the area the robotic arm could reach, the area the orbiter could approach safely. That surrounding space was becoming part of the vehicle. The familiar shape was still learning what it could become. Space Transportation System 41B returned to Earth after almost 8 days, but one of the most important consequences of the mission was waiting only 2 months ahead. In April of 1984, Challenger launched again, Space Transportation System 41C. The crew was Robert Crippen, Francis Scobie, George Nelson, James Van Hoften, and Terry Hart. The mission carried a scientific spacecraft called the Long Duration Exposure Facility. It was designed to remain in orbit for an extended period, exposing experiments and materials to the environment of space. Challenger deployed it. Years later, another shuttle would return to retrieve it. That alone was an expression of the shuttle idea. Put something into orbit now, come back for it later. But Space Transportation System 41C had another target, a satellite called Solar Maximum Mission. It had been launched in 1980. Its purpose was to study the Sun, but several systems had developed problems. Its attitude control system had failed in a way that reduced the spacecraft's ability to point itself properly. The satellite was still in orbit, still valuable, still physically present, but it was not working as intended. Before the shuttle, a damaged satellite in orbit presented a difficult reality. You could communicate with it, you could attempt remote solutions, but if the problem required human hands, those hands were on Earth. Solar Maximum mission offered a different possibility. What if the repair technician could go to the machine? This was the moment when the shuttle began to reveal something stranger than reusability. The orbiter itself could return to space, but perhaps its real power was that it could make other spacecraft less disposable too. The mission plan called for Challenger to rendezvous with Solar Maximum mission. George Nelson would use the manned maneuvering unit. He would fly toward the satellite. He would attach a device to it. Then the shuttle's robotic arm would bring the satellite into the cargo bay. That was the plan. And plans in space sometimes encounter physics with a sense of humor. Nelson approached the satellite. He attempted to attach the capture device. It did not work as intended. The attempt caused the satellite to begin tumbling more rapidly. The object they had come to capture was now rotating. This is an important detail, because it reveals what orbital repair actually means. The satellite was not resting on a workshop table. No one could place a hand on it and ask it politely to remain still. There was no floor beneath it, no clamp already waiting, no convenient pause button. It was a free object. And after the unsuccessful capture attempt, it was a free object rotating in space. Ground controllers worked to stabilize the satellite using its own systems. The next day, the shuttle approached again. This time, Terry Hart used the robotic arm to grapple Solar Maximum mission directly. The satellite was brought into the cargo bay. James Van Hoften and George Nelson performed the repair work. They replaced equipment. The satellite was then returned to orbit. A machine launched in 1980 had been visited by another spacecraft 4 years later. Human beings had approached it, captured it, brought it into a temporary orbital workshop, repaired it, and released it again. This was no longer a demonstration of what the shuttle might someday do. It had done it. The cargo bay had become a repair dock. The robotic arm had become a crane. The astronauts had become orbital technicians, and the shuttle had become something that earlier spacecraft had rarely been designed to become, a place where another spacecraft could be worked on. The familiar shape was still learning what it could become. But there is another layer to this mission, a quieter one: space transportation system. 41C showed that the shuttle's abilities did not operate independently. The orbiter alone was not the repair system. The robotic arm alone was not the repair system. The spacesuits alone were not the repair system. The maneuvering backpack alone was not the repair system. The astronauts alone were not the repair system. The solution emerged from combinations. The orbiter could rendezvous. The crew could go outside. The robotic arm could reach beyond the cargo bay. The cargo bay could hold a large object. Tools could be carried from Earth. A damaged satellite could be approached, captured, worked on, released. The shuttle's flexibility came from the way these abilities could be rearranged. That is one answer to our central question. How did the same spacecraft idea keep becoming a completely different machine without ever changing its basic shape? Because the machine was not defined only by its shape, it was defined by combinations. Change the payload, change the tools, change the crew, change the orbital target, change the sequence of operations, and the same basic vehicle could wake up with a different occupation. On one mission, delivery vehicle. On another, laboratory. On another, repair shop. The transformation did not always require a new spacecraft. Sometimes it required a new arrangement of abilities that were already there. But the year 1984 was only beginning. The shuttle program was moving into a period of increasing flight activity, and the mission names themselves were changing. The simple sequence of early flight numbers had already become less intuitive. The program had adopted a designation system connected to the fiscal year, the launch site, and the planned sequence within that year. The result was a collection of mission names that did not always look chronological when written down. For a person trying to memorize the sequence, this was perhaps the program's first contribution to orbital insomnia. Fortunately, you do not need to memorize it. You can let the names pass. The order matters more than the labels. After Space Transportation System 41C, the next shuttle mission was Space Transportation System 41D, and it introduced another orbiter, Discovery. Discovery would eventually become the most flown spacecraft in the shuttle fleet. But in August of 1984, it had never been to space. Its first launch did not happen on the first attempt, or the second. The mission encountered delays. One launch attempt in June ended only seconds before the planned ignition of the solid rocket boosters. The main engines had begun their ignition sequence. Then the onboard computers detected a problem. The launch was stopped. The solid rocket boosters did not ignite. That distinction mattered enormously. Once the solid rocket boosters ignited, they could not simply be switched off on the launch pad, but the main engines could be shut down before liftoff. The crew remained on the pad. Discovery remained attached to Earth. The mission would wait. Eventually, on August 30th, 1984, Discovery launched on its first flight. The crew was Henry Hartsfield, Michael Coates, Judith Resnick, Stephen Hawley, Richard Mullane, and Charles Walker. The mission deployed 3 communications satellites. It also carried experiments and technology demonstrations. Among them was a large retractable solar array experiment. The array unfolded from the cargo bay. It demonstrated a lightweight structure that could extend to a considerable size. In orbit, large structures present an interesting problem. Rockets prefer compact things. Space often rewards large things. A solar array works by presenting area to sunlight. An antenna may benefit from greater dimensions. A telescope may need a large mirror. A space station may need volumes far larger than any single launch vehicle can carry in final form. So spacecraft designers repeatedly face the same puzzle. How do you place something large inside something narrow? One answer is folding. Another is assembly. The shuttle would eventually become deeply involved in both. On Discovery's first flight, the unfolding solar array experiment was only one small glimpse of that future. The shuttle could carry something compact, open the cargo bay, and allow the object to become larger in space, again. The familiar outline of the orbiter was hiding a changing interior. A cargo bay is an unusual kind of design decision. It is empty space with a promise attached. You do not need to know every future object that will occupy it. You need to know the boundaries, length, width, mass, attachment points, power, thermal conditions, the environment the payload will experience. Within those limits, future engineers can invent new reasons to fly. That is the hidden question beneath the hidden question. Perhaps the shuttle did not need to predict every future mission. Perhaps it only needed to preserve enough useful emptiness. Empty space is easy to underestimate. A room can become many things because it is not permanently filled. A cargo bay can do the same. On one flight, satellites. On another, a laboratory. On another, a telescope. On another, a docking system. On another, a piece of a space station. The emptiness was part of the design. The familiar shape was still learning what it could become. Discovery returned to Earth in September of 1984. Then, only weeks later, Challenger launched again. Space Transportation System 41G, October of 1984. This mission carried 7 people. At that time, the largest crew ever launched aboard a single spacecraft. The crew included Robert Crippen, John McBride, Catherine Sullivan, Sally Ride, David Leesmer, Mark Garneau, and Paul Scully Power. Sally Ride was returning to space. Catherine Sullivan became the first American woman to perform a spacewalk. Mark Garneau became the first Canadian in space. The mission also carried Earth observation instruments. Among them was another shuttle imaging radar experiment. The shuttle was looking down. That phrase sounds obvious. A spacecraft orbits Earth. Of course it can look at Earth, but observation is not merely a matter of opening a window. Different instruments reveal different versions of the planet. Visible light shows one kind of surface. Radar can interact with landscapes differently. It can operate through conditions that limit ordinary optical observation. The shuttle's orbit became a moving platform from which researchers could examine the planet below. Oceans, landforms, atmospheric processes, large-scale features. The spacecraft built to leave Earth was becoming a tool for studying Earth. This is another recurring pattern in spaceflight. Going away can become a way of looking home. Space Transportation System 41G also demonstrated how the shuttle was changing the human scale of orbital flight. 7 people, different roles, different specialties. A spacecraft could now carry pilots, mission specialists, and payload specialists. The crew itself could be configured around the work. The shuttle was not simply carrying more people because more people could fit. A larger crew allowed a mission to contain more kinds of expertise: scientists, engineers, operators, people responsible for particular experiments, people responsible for the vehicle. The mission was becoming a temporary organization in orbit, a small workplace moving around Earth. And yet, the more roles the shuttle accumulated, the more complicated the hidden question became. Flexibility sounds entirely positive. A machine that can do many things appears better than a machine that can do only one. But every new capability brings demands: training, hardware, procedures, integration, testing, mass, time, risk. A spacecraft cannot become infinitely flexible. At some point, every possible job must pass through physical limits: the size of the cargo bay, the lifting capacity of the launch system, the amount of electrical power available, the amount of oxygen and water carried, the endurance of the crew, the reach of the robotic arm, the fuel available for orbital maneuvering, the thermal environment, the geometry of the orbit, the ability to return safely. The shuttle could become many things, but not anything, and that distinction would shape every mission that followed. The familiar shape was still learning what it could become. After Challenger landed, Discovery prepared to fly again. Space Transportation System 51A launched in November of 1984. Only a short time had passed since the previous mission. The pace of shuttle operations was increasing. The crew was Frederick Hawk, David Walker, Joseph Allen, Anna Fisher, and Dale Gardner. The mission began with deployment work. 2 communications satellites were released. But the more unusual task involved 2 other satellites that were already in orbit: Palliper B2 and Westar 6. Both had been deployed earlier in 1984 during Space Transportation System 41B. Both had failed to reach their intended operational orbits after problems with their upper stages. The satellites themselves were not simply gone. They were stranded in orbits that made them unusable for their intended purpose. And now, Discovery was going to retrieve them, not repair them in the cargo bay and release them, bring them home. This was a different answer to the same orbital problem. A satellite could be valuable even after a mission failure. If the shuttle could reach it, perhaps the object itself could be recovered. The crew rendezvoused with the satellites. Astronauts used the manned maneuvering unit. Special capture equipment was involved. The satellites were secured in Discovery's cargo bay, one, then the other. Objects that had once been launched toward their working destinations were now passengers returning to Earth. The cargo bay had reversed its direction. Usually, cargo began on Earth and ended in space. Now, cargo began in space and ended on Earth. This sounds like a small conceptual change. It was not. A launch vehicle traditionally moves useful mass away from the planet. The shuttle could also return significant mass from orbit. Its wings, its thermal protection system, its runway landing, its cargo bay. Together, those features created something rare: downward transportation. Space has always had a delivery problem, but it also has a return problem. Bringing a small capsule back is one thing. Bringing a large satellite back inside a winged spacecraft is another. On Space Transportation System 51A, the shuttle became a retrieval vehicle. The 2 recovered satellites returned to Earth. They were later prepared for new launches. Their stories did not end with the failed deployments. And this gives us another answer to the question we have been carrying. How did the same spacecraft idea keep becoming a completely different machine without ever changing its basic shape? Because direction could change the meaning of the same space. A cargo bay carrying a satellite upward is a delivery system. A cargo bay carrying a satellite downward is a recovery system. The bay has not changed. The direction has. And with that reversal, the mission becomes something new. The familiar shape was still learning what it could become. By the end of 1984, the shuttle had crossed a remarkable distance without travelling beyond low Earth orbit. It had not gone to the moon. It had not travelled to another planet. Its physical range remained close to Earth. But its operational range had expanded. It could deploy, observe, carry laboratories, support spacewalks, allow astronauts to maneuver independently, rendezvous with satellites, capture them, repair them, release them, retrieve them, return them to Earth. This is where the boring question begins to fall away. The boring question is, what could the shuttle carry? The better question is, what kind of relationship could the shuttle create between Earth and orbit? That relationship was becoming two-way. Things could go up. Things could come down. People could reach machines that had once been unreachable. Hardware in orbit could become accessible again. A spacecraft could be treated not only as something launched, but as something that might later be visited. That idea would become enormously important, because a machine in space is exposed to an unforgiving environment. Components fail, gyroscopes wear, electronics age, solar arrays degrade, instruments become obsolete, unexpected problems appear. If every spacecraft must work perfectly from the moment of launch until the end of its life, then every launch is a permanent separation. But if another spacecraft can visit, the relationship changes. A satellite can become a place. A telescope can become a destination. A space station can become a home that is assembled over time. The shuttle was quietly changing the grammar of orbit. Launch was no longer always the final goodbye. Sometimes we could come back. And yet, that ability depended on a severe set of constraints. The shuttle could not simply travel anywhere around Earth at any moment. It had to reach the right orbit, the right inclination, the right altitude, the right position. It had to carry enough propellant. It had to remain within the performance limits of the launch system. It had to survive the thermal conditions of flight. It had to return with enough margin. Every payload had mass. Every maneuver had a cost. Every kilogram placed inside the vehicle changed something else, and the spacecraft itself carried a contradiction. To launch into orbit, it needed to behave like part of a rocket. To survive orbit, it needed to behave like a spacecraft. To return, it needed to survive atmospheric heating. To land, it needed wings. Every capability added something. Every addition had to be carried all the way upward. Even the wings. The shuttle carried its landing system into space on every mission. It carried the structure required for a runway landing even while it was operating where there were no runways. It carried its heat shield into orbit. It carried the hardware needed for re-entry. It carried the future return journey from the moment it left Earth. That is the price of becoming many machines. You must carry the possibility of transformation with you. The familiar shape was still learning what it could become. And now the hidden question has led us towards something deeper. Flexibility is not magic. It is architecture. It comes from decisions made before the future arrives. A large cargo bay, a crew cabin, an airlock, a robotic arm on missions that required it, orbital maneuvering capability, a thermal protection system, wings, a runway landing. None of these features alone explains the shuttle. The important thing is the way they overlap. The cargo bay means little if the vehicle cannot reach the correct orbit. Rendezvous means little if there is no way to interact with the target. A robotic arm means little if the object cannot be brought somewhere useful. A repair mission means little if the crew cannot carry tools and replacement hardware. A retrieval mission means little if the spacecraft cannot return the recovered object to Earth. The system becomes powerful where capabilities meet. That is why Space Transportation System 41C and Space Transportation System 51A matter so much in the early story. One mission repaired a satellite and returned it to service. Another retrieved 2 stranded satellites and returned them to Earth. The shuttle was no longer proving only that it could be reused. It was beginning to make reuse, repair, retrieval, and revisiting part of the wider orbital environment. And this brings us back to the small, strange question beneath the entire program. How did the same spacecraft idea keep becoming a completely different machine without ever changing its basic shape? Because the shape contained interfaces, places where the future could attach itself. The cargo bay could accept different payloads. The robotic arm could interact with different objects. The airlock could support different work outside. The crew could be assembled around different tasks. The orbit could be selected for different destinations. The vehicle remained recognizable. The relationships changed. Perhaps that is why the shuttle can appear simpler in memory than it really was. Memory keeps the silhouette. The missions lived in the details. A white orbiter beside an orange tank. A familiar photograph. Again and again. But inside that repeating image, the purpose kept moving. In February, an astronaut flew untethered. In April, a damaged solar observatory entered the cargo bay and was repaired. In August, a new orbiter flew for the first time. In October, 7 people travelled together while instruments studied Earth. In November, 2 stranded satellites were brought home. 1 year, 5 missions, 5 different expressions of the same architecture. The shuttle was becoming less like a single tool, more like a workshop whose contents change depending on the job. But workshops have limits. A hammer cannot become a microscope simply because both fit inside the same room. A cargo bay cannot erase the laws of physics. A robotic arm cannot reach forever. A crew cannot remain awake forever. A spacecraft cannot carry unlimited mass. An orbit itself imposes rules that no amount of engineering can negotiate away. To understand what the shuttle could become, we now have to understand what it could not escape. The limits were already present on every mission. Hidden inside the fuel, hidden inside the trajectory, hidden inside the heat of re-entry, hidden inside the weight of the wings, hidden inside the enormous energy required to place even a small object into orbit. The shuttle could change its job, but it could not change the universe in which the job had to be done. And that is where our question goes next. The familiar shape was still learning what it could become. Now, we have to find the constraint. Let us go find it. The shuttle could change its job, but it could not change the universe in which the job had to be done. And the universe, for all its apparent emptiness, had rules. Quiet ones, absolute ones. A satellite could be placed into the cargo bay. A laboratory could be installed. A robotic arm could be attached. A crew could train for years. But before any of those things mattered, the entire arrangement had to leave Earth. That was the first constraint. Mass. Everything had mass. The orbiter, the crew, the food, the water, the experiments, the satellites, the tools, the spacesuits, the cameras, the replacement parts. Even the equipment intended to save mass had mass. Every object carried upward had to be accelerated. Every additional kilogram demanded something from the launch system, and the demand did not end when the vehicle reached space. Once in orbit, the shuttle still needed to maneuver. It needed to orient itself. Sometimes it needed to change altitude. Sometimes it needed to approach another object. And eventually, it needed to return. The familiar shape was still learning what it could become, but every new identity had to fit inside the same physical bargain. This is where the story enters 1985. The year would become the busiest in the history of the Space Shuttle program. 9 missions would launch, 9 journeys into orbit in a single calendar year. The pace was remarkable. The orbiters were no longer occasional experimental visitors to space. They were becoming a fleet. Discovery, Challenger, Columbia, and soon, Atlantis. The missions came closer together. Crews overlapped in training. Payloads moved through preparation. Orbiters returned from one flight and entered processing for another. The program was trying to make spaceflight more frequent, more flexible, more useful, but frequency creates its own constraint. A reusable spacecraft does not become ready for another flight merely because it has landed. It must be inspected, serviced, prepared. Its thermal protection system must be examined. Its engines must be maintained. Its systems must be checked. New payloads must be installed. New mission requirements must be integrated. Reusability does not remove work. It changes the kind of work. And so, as the missions of 1985 begin, keep the central question with you. How did the same spacecraft idea keep becoming a completely different machine without ever changing its basic shape? The answer now becomes less romantic, because every transformation required preparation. Every new mission had to be built inside the limits of the same vehicle. Let us begin. The first shuttle mission of 1985 was Space Transportation System 51C. Discovery launched in January. The crew was Thomas Mattingly, Lauren Shriver, Ellison Onizuka, James Buckley, and Gary Payton. The mission was different from those immediately before it. Much of its work was classified. It was the first dedicated space shuttle mission for the United States Department of Defense. The shuttle had become another kind of vehicle, a military space transportation platform. The precise details of classified missions were not always available to the public. That creates an unusual difficulty when telling the history of every shuttle flight. Some missions are documented in extraordinary detail: experiments, deployment sequences, scientific results, photographs, crew activities. Other missions contain deliberate silences. Space Transportation System 51C carried a classified payload. The mission launched into an orbit chosen for its purpose. And even here, the constraint of orbit mattered. A spacecraft cannot simply be launched into any orbital path with equal ease. The latitude of the launch site matters. The direction of launch matters. The desired inclination matters. The performance of the vehicle matters. The payload mass matters. Orbit is not one destination. It is an enormous family of paths. Two spacecraft can both be described as orbiting Earth while traveling through geometries that make meeting each other extremely difficult. The shuttle's flexibility therefore existed inside orbital boundaries. It could become many things, but only after the mission planners answered a more basic question. Where must it go? Discovery completed its mission and returned to Earth. Then, in April, Challenger launched on Space Transportation System 51B. This mission carried Spacelab 3 once again. The cargo bay became a laboratory. The crew included Robert Overmyer, Frederick Gregory, Don Lind, Norman Thagard, William Thornton, Lodewijk van den Berg, and Taylor Wang. 7 people, a laboratory in orbit, experiments in materials science, fluid behavior, life sciences, atmospheric studies, and 2 small squirrel monkeys, named number 384 and number 952. Spaceflight history contains many grand names: Columbia, Challenger, Discovery, Atlantis, and occasionally a squirrel monkey identified by a number. The animals were part of research into how living organisms responded to weightlessness. The mission also carried laboratory rats. The shuttle had become a temporary biological research station. This illustrates another constraint. Human beings are not the only things that behave differently in orbit. Fluids behave differently. Materials behave differently. Flames behave differently. Living systems respond to the absence of the constant gravitational conditions experienced on Earth. A laboratory in orbit is useful precisely because one familiar influence has been greatly reduced. But creating that laboratory is complicated. Experiments need power, temperature control, crew time, storage, data collection, sometimes refrigeration, sometimes containment, sometimes careful handling. The cargo bay may look like empty volume, but scientific work turns volume into infrastructure. The shuttle could carry a laboratory because engineers had created systems that allowed the laboratory to function. Again, flexibility came from interfaces. Power could be provided, data could be handled, people could move between the orbiter and the laboratory. Experiments could be designed around the environment. The familiar shape was still learning what it could become, but each new use consumed resources: space, mass, electricity, time, attention. These are the quiet currencies of a spacecraft. A mission has only so much of each. Then came Space Transportation System 51G Discovery, launched in June of 1985. The crew was Daniel Brandenstein, John Creighton, Shannon Lucid, John Fabian, Stephen Nagel, Patrick Baudry, and Sultan Salman Al Saud. The mission deployed 3 communications satellites. The crew represented a widening international presence aboard the shuttle. Patrick Baudry was from France. Sultan Salman Al Saud became the first Saudi Arabian citizen in space. The shuttle was becoming international in a way that reflected the changing nature of its payloads and partnerships. A communications satellite might serve users far from the launch site. A scientific experiment might involve researchers from several countries. A crew member might represent an international partner. Spaceflight was becoming less easily contained within a single national story, yet the physical constraints remained indifferent to nationality. Every satellite still had mass. Every orbit still required energy. Every mission still had a finite duration. Every landing still required the orbiter to return through the atmosphere. The shuttle could carry a diverse collection of people and machines. Physics did not offer a discount for variety. In July, Challenger launched again, Space Transportation System 51F. The mission was also known as Space Lab 2. The crew was Charles Fullerton, Roy Bridges, Story Musgrave, Anthony England, Carl Hennies, Lauren Acton, and John David Bartow. The launch itself demonstrated how constraints can appear before orbit is even reached. During ascent, one of Challenger's 3 main engines shut down prematurely. The vehicle continued. The mission performed what was known as an abort to orbit. Despite the engine shutdown, Challenger reached a usable orbit. The flight continued. That phrase, abort to orbit, sounds almost contradictory. An abort suggests stopping, orbit suggests arrival. But the shuttle launch system had several possible responses to serious problems during ascent, depending on when a problem occurred. The vehicle might attempt different procedures. In this case, the spacecraft could still reach orbit. Not exactly the originally planned orbit, but an orbit from which the mission could continue. The event revealed something fundamental. The path to space was not a simple vertical climb. The shuttle was accelerating toward orbital velocity. Altitude mattered, but speed mattered even more. Orbit is not achieved merely by going high. A spacecraft must move sideways around Earth fast enough that its path continually falls around the planet. The main engines and solid rocket boosters were not simply lifting the shuttle away from the ground. They were building velocity, an enormous amount of it, and every kilogram had to be accelerated along with the vehicle. This is why mass is such a severe constraint. A heavier payload affects performance. A different orbit affects performance. A higher inclination can affect performance. Mission design becomes a negotiation among desires. What do we want to carry? Where do we want to go? How long do we want to remain there? What maneuvers must we perform? What must come home? The shuttle could not answer every question with yes. Space Transportation System 51F continued with its scientific work. Space Lab 2 carried instruments for astronomy, solar observation, plasma physics, and other research. The shuttle had survived a significant ascent problem and still became a laboratory in orbit. But the event was also a reminder. The flexibility visible in the cargo bay depended on a launch system operating near extraordinary physical demands. The familiar shape was still learning what it could become, and every transformation began with acceleration. Only days after Challenger returned, Discovery launched on Space Transportation System 51 August of 1985. The crew was Joe Engel, Richard Covey, James Van Hoften, John Lounge, and William Fisher, the mission deployed 3 communications satellites, but it also performed another satellite repair. The target was LESAT-3. The satellite had been deployed earlier that year during Space Transportation System 51D. Its systems had failed to activate properly. Now Discovery approached it. Astronauts James Van Hoften and William Fisher went outside. The satellite was captured, worked on, and returned to operation. The repair required multiple spacewalks. Once again, the shuttle had become a workshop. But compare this repair with Solar Maximum mission. The target was different, the hardware was different, the repair procedure was different, the tools were different, the crew training was different. This is where the idea of a flexible spacecraft can become misleading. The shuttle did not automatically know how to repair satellites. There was no universal repair button. Every target created a new engineering problem. How do you capture this object? Where can an astronaut hold it? How does it move? What failed? What tools are needed? Can the work be performed while wearing a pressurized spacesuit? Can the satellite be stabilized? Can the robotic arm reach the necessary location? Can the entire procedure fit within the mission timeline? The vehicle provided possibilities. People had to turn those possibilities into a specific plan. The familiar shape was still learning what it could become. But the learning happened mission by mission. Then, in October of 1985, a new orbiter flew, Atlantis, Space Transportation System 51J, its first mission. The crew was Carol Bobko, Ronald Grabe, David Hilmers, Robert Stewart, and William Pales. Like Space Transportation System 51C, this was a dedicated mission for the United States Department of Defense. Its primary payload was classified. Atlantis entered the fleet as the 4th space-worthy orbiter of the operational era. Columbia, Challenger, Discovery, Atlantis, 4 spacecraft, similar in appearance, not identical in history. Each would accumulate its own sequence of missions, its own repairs, its own modifications, its own place in the program. The fleet concept introduced another form of flexibility. A mission did not always depend on one specific orbiter forever. Different vehicles could be prepared for different flights. Schedules could be arranged across the fleet. But again, more vehicles meant more processing, more maintenance, more hardware, more facilities, more people. A fleet is not simply 4 times 1 spacecraft. It is a network. And networks create dependencies. The launch pads, the vehicle assembly building, the crawler transporters, the external tanks, the solid rocket boosters, the main engines, the processing facilities, the tracking systems, the mission control teams, the recovery ships for the boosters, the manufacturing chain, the contractors, the engineers, the technicians, the weather forecasts, the runways. The shuttle seen on television was only the visible tip of a much larger machine. This may be the most important constraint of all. The orbiter could fly only because an enormous system on Earth allowed it to fly. The familiar shape was still learning what it could become, but it never became independent. In October, Challenger launched again, Space Transportation System 61A. The mission carried Spacelab D1. The letter D referred to Germany. The flight was a major West German-sponsored scientific mission. 8 people travelled aboard Challenger. It was the largest crew ever launched aboard a single spacecraft, and it remained the largest crew launched aboard one spacecraft throughout the shuttle era. The crew included Henry Hartsfield, Stephen Nagel, Bonnie Dunbar, James Buckley, Guillaume Bluford, Reinhard Furrer, Ernst Messerschmidt, and Wubbo Ockels. The laboratory operated around the clock. The crew worked in shifts. This is another way to increase the productivity of a mission. Not by making the spacecraft larger, not by making the mission infinitely longer, by using time differently. While some crew members slept, others worked. The laboratory continued. Experiments continued. The orbit continued. The sun rose and set repeatedly outside. A spacecraft in low Earth orbit can experience many sunrises and sunsets in a single Earth day. Human schedules must therefore be created artificially. work periods, sleep periods, meals, exercise, experiment timelines, communications. The natural rhythm of daylight is no longer a reliable clock. Time itself becomes a resource to schedule. 8 people aboard one orbiter also meant 8 human beings requiring air, water, food, sleeping arrangements, hygiene, and space. The shuttle could carry a larger crew, but every additional person was also a payload with needs. Humans are scientifically interesting cargo. We are also extremely demanding cargo. We prefer oxygen, reasonable temperatures, water, food, waste management, and occasionally, sleep. The shuttle had to support all of it. The mission completed dozens of experiments: materials science, biology, physics, technology. The cargo bay had become an international laboratory. The crew cabin had become a shift-based workplace. The same orbiter that had previously carried satellites now carried a complex scientific program. Again, the central question returns. How did the same spacecraft idea keep becoming a completely different machine without ever changing its basic shape? By changing what occupied its limited resources. Mass became satellites on one mission, laboratory equipment on another, crew members on another, repair tools on another. The spacecraft could become many things because its resources could be reassigned, but they could not be made infinite. That is the constraint. Flexibility is the art of choosing what the limits will be used for. The familiar shape was still learning what it could become. In November of 1985, Atlantis flew again. Space Transportation System 61B. The crew was Brewster Shaw, Brian O'Connor, Mary Cleave, Sherwood Spring, Jerry Ross, Rodolfo Neri Vela, and Charles Walker. The mission deployed communications satellites, but another experiment pointed toward the distant future of the shuttle. Astronauts constructed large framework structures in the cargo bay during spacewalks. The experiments were known as experimental assembly of structures in extravehicular activity. The name was practical. The idea was profound. Could astronauts assemble large structures in space? Not merely repair a machine, not merely retrieve one, build something, piece by piece. The astronauts worked with structural elements designed for assembly and weightlessness. This was a rehearsal for a future that did not yet exist. Years later, shuttle crews would help assemble the International Space Station. Large components would arrive separately. Astronauts would connect hardware, move equipment, install structures, route connections, work outside for hours. In 1985, that future was still ahead, but the question was already being tested in the cargo bay. How efficiently can a human being build in space? A structure that is easy to assemble on Earth may not be easy to assemble while wearing a pressurized spacesuit. Gloves reduce dexterity. The suit resists movement. The astronaut must remain restrained. Tools must not drift away. Parts must be controlled. Every action creates reaction. The absence of weight does not mean the absence of mass. A large object may feel weightless, but once moving, it still has momentum. Stopping it requires force. Controlling it requires planning. Construction in space therefore follows a different physical intuition. The shuttle cargo bay became a classroom. The astronauts became builders. The structure did not need to become a permanent station. The experiment itself was the mission. Learn how people work. Learn how long tasks take. Learn what tools are effective. Learn what designs cooperate with gloved hands. The familiar shape was still learning what it could become. But now, it was also teaching humans what they could become. Pilots, scientists, repair technicians, satellite retrievers, construction workers in orbit. The year 1985 was nearing its end. 9 shuttle missions had flown. Discovery, Challenger, Atlantis. A remarkable operational tempo. The program had carried classified payloads, scientific laboratories, communication satellites, international crews, repair equipment, construction experiments. The shuttle seemed to be fulfilling its promise of flexibility, but this is exactly where constraints become easiest to forget. Success can hide them. When flights happen repeatedly, the extraordinary begins to acquire a schedule. When a spacecraft lands and later flies again, reuse begins to look normal. When crews return safely, risk becomes less visible. When complicated procedures work, the complexity can disappear behind the result. A satellite is deployed, a mission is complete. An orbiter lands, another rolls toward the pad. The system begins to look inevitable, but it was never inevitable. Every launch remained a controlled encounter with enormous energy. Every ascent depended on thousands of components. Every mission depended on weather, hardware, software, human decisions, materials, manufacturing, inspection, communication, and physical laws that did not become more forgiving simply because the flight number increased. The familiar shape was still learning what it could become. And then came January of 1986. Before we arrive at the mission, most people remember from that month. There was another shuttle already in orbit, Columbia, Space Transportation System 61C. It launched on January 12th, 1986. The crew was Robert Gibson, Charles Bolden, Franklin Chang Diaz, Stephen Hawley, George Nelson, Robert Senker, and Bill Nelson. Columbia had not flown since Space Transportation System 9 in late 1983. During the years between, it had undergone modifications. Now it returned. The mission deployed a communications satellite. It also carried experiments. Among the crew was Bill Nelson, a member of the United States House of Representatives at the time, flying as a payload specialist. The launch had experienced delays before finally taking place. Weather, technical issues, the kinds of factors that repeatedly shape launch schedules. Once in orbit, the mission continued. Columbia returned to Earth on January 18th. 10 days later, another shuttle stood on another launch pad. Challenger, Space Transportation System 51L, January 28th, 1986. The crew was Francis Scobie, Michael Smith, Ronald McNair, Ellison Onizuka, Judith Resnick, Gregory Jarvis, and Krista McAuliffe. McAuliffe was a teacher. The Teacher in Space project had brought enormous public attention to the mission. Students watched, schools watched, families watched. The flight was intended to carry a communications satellite. It also carried scientific work. But 73 seconds after liftoff, Challenger was lost. All 7 crew members died. The cause would be investigated in detail. The immediate physical failure involved seals called O-rings in a joint of the right solid rocket booster. The unusually cold conditions before launch affected their performance. Hot gas escaped the joint. The failure led to the destruction of the vehicle, but a technical description alone is not enough to understand the event, because hardware exists inside organizations. Measurements are interpreted by people. Concerns are communicated. Schedules create pressure. Decisions are made. The investigation led by the Presidential Commission on the Space Shuttle Challenger accident examined not only the failed hardware, but the decision-making process surrounding the launch. The accident revealed that a constraint can be physical long before an organization fully respects it. Rubber changes behavior with temperature. A seal does not care about a launch schedule. A joint does not respond to optimism. Cold is not persuaded by experience. The familiar shape had reached a limit, and the limit had been there before the launch. This is the difficult truth of constraints. They do not appear only when something fails. They are present during every success. The O-rings had existed on earlier flights. The joint design had existed. Evidence of erosion and blow-by had appeared before. The system had been giving information. But information does not interpret itself. People must decide what it means. After Challenger, the shuttle fleet stopped flying. The program entered a long pause. There would be no shuttle mission in 1987. There would be no shuttle mission for most of 1988. The busiest year in shuttle history had been followed by silence. That silence changed the program. Hardware would be redesigned. Procedures would be reconsidered. management and safety practices would be examined. The solid rocket booster field joints would be redesigned. The shuttle would return, but it would not return unchanged. And yet, from a distance, it would still look familiar. That may be the strangest part. The same white orbiter, the same broad wings, the same vertical launch, the same orange external tank, the same two solid rocket boosters. To an observer, the shape would appear almost continuous. Inside the system, much had changed. This brings us back to the question we have carried from the beginning. How did the same spacecraft idea keep becoming a completely different machine, without ever changing its basic shape? Sometimes because the most important changes were invisible from outside: a redesigned joint, a revised procedure, a new rule, a different launch decision process, a changed escape system, a new understanding of what could go wrong. Machines evolve not only by acquiring new abilities, they evolve by remembering failure. The familiar shape was still learning what it could become. But now, learning had acquired a terrible cost, and we should not rush away from that. 7 people boarded Challenger: Francis Scobie, Michael Smith, Ronald McNair, Ellison Onizuka, Judith Resnick, Gregory Jarvis, Krista McAuliffe. They were not symbols while they were alive. They were people. They had families, colleagues, friends, private habits, ordinary mornings, work to do. The history of a spacecraft program can become crowded with hardware: engines, boosters, tiles, payloads, orbits. But the machine existed because people entered it, and the loss of Challenger changed the meaning of every mission that followed. When the shuttle returned to flight, it would carry more than payload. It would carry memory. The program had encountered the difference between flexibility and invulnerability. They are not the same. A spacecraft can perform many jobs and still have boundaries. A system can succeed repeatedly and still contain unresolved problems. A schedule can become frequent without becoming ordinary. The universe does not adjust its rules to match our confidence. The familiar shape was still learning what it could become. And this is the constraint in full. Not simply mass, not simply fuel, not simply orbit, not simply temperature. The deepest constraint is that every complex machine must operate in the real world. Materials have properties, humans have limits, organizations have weaknesses. Information can be incomplete, warnings can be misunderstood. Components can behave differently under different conditions. A system containing millions of parts can be defeated by a small region of material that does not seal quickly enough in the cold. Scale can be deceptive. The shuttle stack was enormous. The critical failure began in a joint. The vehicle carried people hundreds of kilometers above Earth. The decisive physical process occurred across a distance small enough to hold in your hand. This is why engineering spends so much time on details. The universe often hides consequences inside them. And now, the central question changes again. We began by asking how one spacecraft could become so many different machines. But perhaps we also need to ask something quieter. How much complexity can one machine carry before its flexibility becomes another kind of burden? Every new mission adds procedures, every new payload adds interfaces, every new capability adds training, every new flight adds experience. But experience itself can become dangerous if repeated success is mistaken for proof that a known problem is harmless. A machine can teach people the wrong lesson when it survives. A component may show damage and still complete the mission. The flight succeeds, the damage is inspected, the next flight succeeds, and gradually, an abnormal condition can begin to feel normal. The physical constraint has not changed, only the human interpretation has. This is where the story of the shuttle becomes more than a sequence of missions. It becomes a story about how people understand complicated systems. A reusable spacecraft returns with evidence. That is one of the advantages of reuse. Hardware comes home. Engineers can inspect it. Tiles can be examined. Engines can be removed. Components can be studied. Wear can be measured. But evidence is useful only if it changes understanding. The shuttle could return from orbit. The harder task was returning from assumptions. After Challenger, assumptions had to be reconsidered. The pause lasted 32 months. During that time, the shuttle did not fly, but the program did not stop working. Investigators examined the accident. Engineers redesigned hardware. Procedures changed. The relationship between the shuttle and its future missions changed. Some planned payloads would move to other launch vehicles. The idea of routine access to space had been deeply challenged. When the shuttle eventually returned, the mission would have a simple designation: Space Transportation System, 26, Discovery, September of 1988. But we are not there yet. For now, the launch pads are quiet. The orbiters remain on Earth. The cargo bays are closed. The robotic arms are still. No satellite is being captured. No laboratory is circling the planet inside an orbiter. No crew is preparing to land after days in weightlessness. The fleet has stopped. And in that silence, the real problem can finally be seen in full. The shuttle was designed to do many things, but everything it did depended on the same chain: launch, ascent, orbit, re-entry, landing. A mission could contain the most sophisticated telescope ever built, the most valuable satellite, the most carefully designed experiment, the most experienced crew, but none of those things could escape the chain. A failure in one stage could erase every purpose that came after it. That is the nature of a system. The mission is only as possible as the path that carries it. The familiar shape was still learning what it could become. And now, before the shuttle can become a telescope launcher, a planetary probe carrier, a radar observatory, a bridge to a Russian space station, and eventually a construction vehicle for the International Space Station, it must first become something more difficult, a spacecraft that can return after losing one of its own. The constraint has shown itself. The next question is what happens when that constraint is not respected. The problem is no longer hidden. It is waiting in full. Let us wonder about it. For 32 months, no space shuttle left Earth. The launch pads remained. The orbiters remained. The buildings remained. The people remained. But the rhythm had stopped. This is what a complex system looks like when one part of its story becomes impossible to ignore. Before Challenger, the shuttle program had been accelerating. 9 missions in 1985. Another mission already completed in January of 1986. Launches had begun to appear close together. Orbiters moved through processing. Crews moved through training. Payloads moved toward flight. The program was becoming busy enough that the extraordinary could almost resemble transportation. Then, 73 seconds changed the rhythm. The problem was no longer simply a failed seal. It was not simply a damaged booster joint. It was not simply cold weather. Those things mattered, but the problem in full was larger. The shuttle had been asked to become many machines: a satellite launcher, a laboratory, a repair shop, a retrieval vehicle, a military platform, a construction test bed, an international workplace, and every one of those identities depended on the same launch system, the same basic path away from Earth, the same need to survive ascent, the same need to return. Flexibility had created many purposes, but those purposes rested on shared vulnerabilities. That is the strange architecture of a general-purpose spacecraft. Many missions can be different. The consequences of one common failure can be the same. The familiar shape was still learning what it could become, and now it had to learn what could not be allowed to become familiar. During the pause, the Challenger accident was investigated. The solid rocket booster joints received intense attention. The field joint design was changed. The redesign added features intended to improve sealing and prevent the kind of failure that had occurred. The shuttle program also underwent broader changes: safety, management, launch decision-making, crew escape provisions, processing. The return to flight would not be a simple continuation. It would be an attempt to resume the program with a different understanding of the machine. That distinction matters. A spacecraft can look nearly identical from a distance while becoming meaningfully different inside its procedures. The public sees the launch, the flame, the rising vehicle, the curve into the sky. But much of safety is invisible. A redesigned component does not announce itself in a photograph. A changed review process has no silhouette. A new requirement does not leave a trail of smoke. Yet those invisible changes can determine whether the visible machine flies. The familiar shape was still learning what it could become, and sometimes, becoming safer does not look dramatic at all. It looks like a meeting that lasts longer, a question asked again, a concern that is not dismissed, a test repeated, a component redesigned, a launch delayed, a person saying no. Spaceflight is full of spectacular images. Safety is often made of very unspectacular decisions. For more than 2 years, those decisions accumulated. Then came September of 1988. Discovery stood on Launch Pad 39B. The mission was Space Transportation System 26. The crew was Frederick Hawk, Richard Covey, John Lounge, David Hilmers, and George Nelson. All 5 were experienced astronauts. The mission carried a tracking and data relay satellite, but the payload was only part of the meaning. The deeper purpose was contained in 3 quiet words: return to flight. Discovery launched on September 29th, 1988. The shuttle was flying again. It is tempting to describe such a moment as a reset, but history does not reset. A vehicle can return to the launch pad. A program can resume. A new crew can enter orbit. But the past remains inside the future. The launch of Discovery did not erase Challenger. It could not. Instead, the return to flight carried the accident forward as knowledge. This is one of the difficult things engineering must do. Remember without becoming motionless. Continue without pretending nothing happened. The shuttle had to fly again if the program was to continue, but it could not fly again as though January of 1986 belonged to another universe. Space Transportation System 26 completed its mission. Discovery deployed the tracking and data relay satellite. The crew performed experiments. After 4 days, the orbiter returned to Earth. 1 mission, 1 safe return. The silence had been broken, but 1 successful flight could not answer every question. The program now entered a slower rebuilding of operational confidence. The next mission launched in December. Atlantis, Space Transportation System 27. The crew was Robert Gibson, Guy Gardner, Richard Mullane, Jerry Ross, and William Shepard. The mission carried a classified payload for the United States Department of Defense. Much of the work remained secret, but one part of the mission later became especially important to the history of the shuttle's thermal protection system. During launch, debris struck Atlantis. The orbiter's heat shield suffered significant tile damage. The crew observed the damage in orbit. Images were transmitted to the ground, but the severity was not fully understood before re-entry. Atlantis returned safely. After landing, the damage could be examined directly. 1 tile had been lost entirely. A metal plate beneath that location helped protect the vehicle. The orbiter survived. This was a success. But success can contain a warning. The shuttle's thermal protection system existed because returning from orbit creates extraordinary heating. The orbiter entered the atmosphere at tremendous speed. The air ahead of the vehicle was compressed and heated. The surface experienced conditions that ordinary aircraft do not encounter. The black tiles and other thermal protection materials were not decoration. They were part of the path home, and they were vulnerable. A spacecraft built for reuse had to carry its heat shield on every flight. That shield had to survive launch, orbit, the environment of space, and then re-entry. The same surface that protected the orbiter during return could be damaged during ascent. This is the problem in full. The stages of a mission are not isolated from one another. What happens during launch can affect re-entry. What happens in orbit can affect landing. A piece of debris released early in the flight can create a problem that remains hidden until much later. A mission is a chain through time. The familiar shape was still learning what it could become, but the shape had to survive every transformation. Atlantis landed safely in December. The shuttle program entered 1989. The first mission of the year was Space Transportation System 29. Discovery launched in March. The crew was Michael Coates, John Blaha, James Buckley, Robert Springer, and James Bargian. The mission deployed another tracking and data relay satellite. These satellites form part of a communications network that improve contact between spacecraft and the ground. This may sound less dramatic than a spacewalk. There is no astronaut floating above Earth, no satellite being captured, no enormous telescope, but communication is one of the hidden systems that makes other missions possible. A spacecraft can be physically healthy and still be operationally limited if communication is poor. Data must come down, commands must go up. Voice must travel between crews and controllers. Scientific observations must reach researchers. The shuttle itself depended on a wider infrastructure: ground stations, relay satellites, tracking networks, mission control. The spacecraft was not alone simply because it was in orbit. This is another part of the problem. Complex systems depend on other complex systems. A shuttle mission was never only the orbiter, it was also the network surrounding it. The familiar shape was still learning what it could become, but it was always connected to something larger. In May of 1989, Atlantis launched on Space Transportation System 30. The crew was David Walker, Ronald Grabe, Norman Thagard, Mary Cleave, and Mark Lee. Inside the cargo bay was a spacecraft that would not remain near Earth, Magellan. Its destination was Venus. The shuttle itself would not go there. That was not what it was built to do. Instead, Atlantis carried Magellan into low Earth orbit. Then an upper stage sent the spacecraft onward. This is an elegant division of labor. The shuttle could carry people and cargo into orbit. A separate propulsion stage could send an uncrewed spacecraft farther away. The orbiter became the first step in a much longer journey. Magellan would eventually use radar to map the surface of Venus in extraordinary detail. The planet is hidden beneath thick clouds. Visible light cannot simply reveal the surface from orbit. Radar can. Years earlier, shuttle missions had carried radar instruments for observing Earth. Now, a spacecraft launched from the shuttle would use radar to reveal another world. The cargo bay had become a departure point for planetary exploration. The familiar shape was still learning what it could become, but here the constraint becomes especially clear. The shuttle could not become an interplanetary spacecraft. Its own operational environment remained near Earth. It could not fly to Venus. It could not carry a crew to Mars. It could not simply point itself toward Jupiter and continue. Its systems, its propellant, its thermal design, its life support, its communications, its entire architecture belonged to a different kind of mission. So instead of becoming everything, the shuttle became part of something. It carried Magellan to the place where another vehicle could take over. This is an important answer to our central question. How did the same spacecraft idea keep becoming a completely different machine without ever changing its basic shape? Sometimes, by accepting that it would only perform one section of the journey, a machine does not need to do everything to change what becomes possible. It needs to connect with the next machine. Atlantis returned to Earth. Magellan continued toward Venus. Two spacecraft that had begun the mission together now followed completely different futures. One came home, one left Earth behind. Then, in August of 1989, Columbia launched on Space Transportation System 28. The crew was Bruce Shaw, Richard Richards, James Adamson, David Leesmer, and Mark Brown. The mission was dedicated to the United States Department of Defense. Its primary payload was classified. Again, the public record contains less detail than for many scientific missions, but the flight itself contributes to the larger pattern. The shuttle program served multiple institutions: civil science, commercial satellite deployment, national security, international research, planetary exploration. The same fleet was expected to support very different purposes. That diversity was a strength. It was also a burden. Different missions created different requirements, different orbits, different payloads, different security rules, different training, different hardware. The shuttle was flexible because it could accommodate variation. But variation had to be managed. Nothing entered the cargo bay casually. A payload had to survive launch loads. It had to be compatible with the orbiter. Its electrical requirements had to be understood. Its structural connections had to be designed. Its behavior in an emergency had to be considered. Its effect on the mission had to be calculated. Even a payload that never moved during flight could change the spacecraft simply by being there. Mass changes performance. Mass distribution matters. Every object participates in the mission, whether it is active or silent. The familiar shape was still learning what it could become, but every new identity had to be engineered into existence. In October of 1989, Atlantis launched again. Space Transportation System 34. The crew was Donald Williams, Michael McCulley, Franklin Chang Diaz, Shannon Lucid, and Ellen Baker. The primary payload was Galileo, another spacecraft bound for the planets. Its ultimate destination was Jupiter. Again, Atlantis would not go with it. The shuttle carried Galileo into orbit. An upper stage then sent the spacecraft away from Earth. But Galileo's path to Jupiter was not a simple straight line. The spacecraft would use gravity assists. It would pass Venus, then Earth again. Each encounter would change its trajectory and speed relative to the Sun. A journey to Jupiter could therefore include a visit to the inner solar system. Orbital mechanics has a quiet way of making maps look misleading. The shortest line on paper is not always the practical path through space. Energy matters. Planetary motion matters. Timing matters. A spacecraft can borrow momentum through a carefully planned gravitational encounter. Nothing is free, but trajectories can be clever. Galileo began a journey that would last years. Atlantis returned after several days. Again, the shuttle had served as a temporary harbour for a spacecraft whose story would become much longer than its own mission. The cargo bay doors opened, a machine left, the doors closed, the orbiter came home, Galileo continued. Years later, it would reach Jupiter. It would send a probe into the giant planet's atmosphere. It would study Jupiter and its moons. It would observe worlds that the shuttle itself could never approach. The shuttle's range was limited. Its influence was not. The familiar shape was still learning what it could become. And this is where the problem in full becomes interesting. A machine can overcome some limits by becoming part of a chain. The shuttle could not fly to Jupiter, so it carried a spacecraft that could. The shuttle could not remain permanently in orbit, so it could carry equipment for platforms that would. The shuttle could not perform every scientific experiment itself, so it carried laboratories. It could not become a satellite, so it deployed satellites. It could not be everywhere, so it helped place other machines where they needed to go. The solution to limitation was often cooperation between machines, but cooperation creates interfaces, and interfaces create possible failures. A satellite must separate correctly, an upper stage must ignite correctly, a payload must communicate, a robotic arm must grapple, a docking system must seal, a structural connection must hold. Every connection is useful. Every connection is also a place where something must work. The more capable the system becomes, the more carefully those boundaries must be understood. Then came November of 1989. Discovery, Space Transportation System 33. The crew was Frederick Gregory, John Blaha, Story Musgrave, Catherine Thornton, and Manley Carter. The mission was another dedicated flight for the United States Department of Defense. Its primary payload was classified. The launch had been delayed. Eventually, Discovery reached orbit. The mission was completed. The orbiter returned. By the end of 1989, the shuttle had completed 5 missions during the year. The fleet was operating again, not at the pace of 1985, but steadily. Discovery had carried a relay satellite. Atlantis had launched Magellan toward Venus. Columbia had flown a classified mission. Atlantis had launched Galileo toward Jupiter. Discovery had flown another classified mission. The shuttle had returned from its long pause and immediately resumed becoming different things. Communications vehicle, planetary launch platform, military spacecraft. Again, the silhouette remained familiar, the missions did not. But the problem revealed by Challenger had not disappeared simply because flights resumed. The deeper problem remained. How do you operate a spacecraft that is both reusable and extraordinarily complex? How do you preserve caution when missions become frequent? How do you distinguish acceptable damage from a warning? How do you prevent yesterday's survival from becoming tomorrow's assumption? These questions do not have one permanent answer. A system changes. Hardware ages. People change roles. Organizations change. New missions create new conditions. New evidence appears. Safety is not a box that can be checked once. It is a process that must continue while everything else continues too. The familiar shape was still learning what it could become, and the learning never ended. In January of 1990, Columbia launched on Space Transportation System 32. The crew was Daniel Brandenstein, James Weatherby, Bonnie Dunbar, David Lowe, and Marcia Evans. The mission deployed a communications satellite, but its second major objective returned us to an object we met years earlier, the Long Duration Exposure Facility. It had been deployed by Challenger during Space Transportation System 41C in April of 1984. It had remained in orbit for nearly 6 years. Its purpose was written into its name, Long Duration Exposure. The spacecraft carried experiments and materials designed to experience the space environment over an extended period. Atomic oxygen, radiation, micrometeoroids, thermal cycling, the repeated transition between sunlight and darkness. Space can appear empty. For materials, it is an environment. Surfaces change, coatings degrade, tiny impacts occur, radiation accumulates. The Long Duration Exposure Facility had spent years collecting those effects. Now Columbia approached it. The shuttle's robotic arm captured the facility. The large structure was brought into the cargo bay. And then, it came home. This retrieval was different from the rescue of stranded communications satellites. The Long Duration Exposure Facility had completed its intended work. Its return was part of the experiment. Scientists needed the hardware back. The surfaces themselves contained information. A spacecraft that could return large objects from orbit made a particular kind of science possible. Expose materials to space, wait, retrieve them, study them on Earth. The cargo bay became a bridge between laboratory environments. The experiment began on Earth, continued in orbit for years, then returned to laboratories on Earth. The shuttle did not merely carry the experiment, it completed the loop. The familiar shape was still learning what it could become. This mission brings us to a deeper version of the central question. How did the same spacecraft idea keep becoming a completely different machine, without ever changing its basic shape? Because a mission was not defined only by what happened during the days the shuttle was in orbit. Some missions connected events separated by years. Deploy now, retrieve later, launch a planetary spacecraft now, receive its discoveries years later, carry an experiment whose scientific meaning will be understood after the orbiter has landed. The shuttle mission could be only one chapter in a much longer process. Space Transportation System. 32 ended with Columbia returning to Earth. The Long Duration Exposure Facility returned with it. An object placed into orbit by Challenger had been retrieved by Columbia. One orbiter began the experiment, another completed it. The fleet itself had created continuity across years, and that is another answer. The same spacecraft idea could become different machines because the program was larger than any single orbiter. Columbia could finish work begun by Challenger. Discovery could carry a relay satellite used by future missions. Atlantis could launch a probe that would communicate with Earth long after the shuttle mission ended. Each flight inherited infrastructure from earlier flights. Each flight could create possibilities for later ones. The missions were separate, the system was continuous, but continuity can hide accumulation. Every flight leaves something behind: experience, data, where, procedures, confidence, concerns, lessons. Sometimes hardware in orbit, sometimes hardware returned to Earth. The problem in full is not simply preventing one known failure from happening again. It is learning how to notice the next problem before it becomes familiar. That is much harder. Known failures can be redesigned, unknown failures have not yet introduced themselves, and complex machines are very good at finding new ways to surprise the people who built them. The shuttle had millions of components, Thousands of thermal protection tiles, 3 main engines, 2 solid rocket boosters, 1 external tank, flight computers, hydraulic systems, electrical systems, life support, payload systems, landing gear, control surfaces, windows, doors, valves, pumps, sensors, software, wiring. Every mission required these systems to work together across environments that changed dramatically within minutes. On the launch pad, gravity held the vehicle down. During ascent, acceleration increased, the atmosphere thinned, the boosters separated, the external tank separated. In orbit, the cargo bay doors opened. The thermal environment changed as the spacecraft moved between sunlight and darkness. Before return, the doors closed. The orbiter turned. The engines performed a de-orbit burn. The vehicle encountered the atmosphere. The heat increased. The air thickened. Control shifted. The spacecraft became a glider. The landing gear came down. The runway approached. One vehicle. Many physical regimes. The familiar shape was still learning what it could become. But perhaps the more important truth is this. The shape had to survive becoming all of them. That was the problem in full, not merely launching, not merely orbiting, not merely landing, transitioning, again and again. Rocket to spacecraft, spacecraft to re-entry vehicle to glider, glider to machine on a runway. Then, after landing, back into a vehicle that could be prepared to fly again. Every transition contained interfaces. Every interface contained uncertainty. A reusable spacecraft had to pass through the entire sequence repeatedly. The very feature that made the shuttle extraordinary also made its safety problem unusually complicated. It did not perform one difficult act. It performed several different difficult acts in sequence, and then it was expected to do them again. The familiar shape was still learning what it could become. So our strange question remains. How did the same spacecraft idea keep becoming a completely different machine, without ever changing its basic shape? The answer is no longer only flexibility, it is continuity under transformation. The orbiter had to remain one vehicle while behaving like several. Its cargo could change, its crew could change, its orbit could change, its purpose could change, but the chain of survival could not be broken. That is why a small component can matter as much as a large payload. The mission may be about Jupiter, but a seal still matters. The mission may be about Venus, but a tile still matters. The mission may be classified, but a valve still matters. The mission may carry years of scientific planning, but the landing gear still has to work at the end. Purpose does not outrank physics. The grandest mission and the quietest component share the same spacecraft. And this is where we begin to see the next force shaping the shuttle. The enemy was not one thing. It was not simply gravity. Gravity made orbit possible as well as difficult to reach. It was not simply the atmosphere. The atmosphere created dangerous heating, but it also allowed wings and control surfaces to work during the return. It was not simply complexity. Complexity created capability. The real enemy was subtler, damage that looked survivable, warnings that became ordinary, small uncertainties repeated until they felt familiar. Schedule pressure, incomplete information, the tendency of successful outcomes to soften the memory of how close a system may have come to failure. A spacecraft can survive a problem and accidentally teach people that the problem is safe. That may be one of the most dangerous lessons a successful machine can give. And the shuttle would continue flying. It would launch a telescope that changed astronomy. It would carry observatories that looked at the universe in forms of light human eyes cannot see. It would return to that telescope again and again. It would dock with a Russian space station. It would help build another station piece by piece. It would fly missions longer and more complex than its earliest crews had experienced. The machine would continue becoming, but the enemy would travel with it, not visible in every photograph, not present in every component, sometimes hiding in foam, sometimes in a seal, sometimes in a decision, sometimes in the quiet space between evidence and belief. The familiar shape was still learning what it could become. And now, we have to meet what was always working against it. Let us go find it. The enemy was not one thing. That would have been easier. A single enemy can be named, measured, watched, perhaps even defeated. But the Space Shuttle did not travel through a world with one obstacle. It traveled through layers of them. Gravity resisted the climb. The atmosphere resisted the speed. Heat threatened the return. Cold changed materials. Vacuum changed fluids. Radiation affected electronics and living tissue. Tiny particles crossed orbit at extraordinary relative velocities. Mechanical parts wore. Electronic parts aged. Humans became tired. Organizations became accustomed to success. Schedules became crowded. Information arrived incomplete. And sometimes, the most dangerous condition was not a dramatic failure. It was a small problem that had happened before. A problem the spacecraft had survived. The familiar shape was still learning what it could become. But every new mission entered the same quiet contest. Capability against limitation. Knowledge against uncertainty. Preparation against everything that had not been predicted. The year was 1990. Columbia had just returned with the long-duration exposure facility. An experiment had spent nearly 6 years in orbit and come home. The shuttle had demonstrated again that it could close a loop between Earth and space. Then, in April, Discovery prepared to carry something that would change the way humanity saw the universe. Space Transportation System. 31. The crew was Lauren Shriver, Charles Bolden, Bruce McCandless, Catherine Sullivan, and Stephen Hawley. Inside Discovery's cargo bay was the Hubble Space Telescope. The telescope had been conceived long before this mission. Its development had taken years. Its launch had been delayed by the interruption in shuttle flights after Challenger. Now, on April 24th, 1990, Discovery lifted from Florida. The telescope traveled inside the cargo bay, folded, protected, waiting. Hubble was designed to observe the universe from above most of Earth's atmosphere. That atmosphere keeps us alive. It also complicates astronomy. Air moves, temperature changes, light is distorted. Some forms of radiation from space are absorbed before reaching the ground. A telescope above the atmosphere can observe with a different kind of clarity. But placing a large observatory in orbit creates another problem. Once it is there, what happens if something goes wrong? Hubble had been designed with servicing in mind. That decision would become one of the most important in the history of the shuttle. The telescope was not meant to be an untouchable object. Components could be replaced, instruments could be changed, astronauts could visit. The observatory was a spacecraft, but it was also a destination. Discovery reached the planned orbit. The cargo bay doors were open. The robotic arm lifted Hubble from the bay. The telescope was released. A new observatory began its life above Earth. The mission was a success, but soon, scientists discovered a serious problem. The images were not as sharp as expected. The primary mirror had been manufactured to the wrong shape. The error was tiny. The consequences were not. This is the enemy in one of its purest forms: scale. A very small physical error can create a very large scientific problem. The mirror was enormous compared with the manufacturing error, but light is not impressed by the size of a telescope's ambitions. Optics obey geometry. A surface that is wrong by a tiny amount can send light to the wrong place. The telescope was in orbit. The mirror could not simply be removed and polished again. Years of work had reached space carrying a flaw. And yet, Hubble had been designed to be serviced. The shuttle had already demonstrated satellite repair. It had already shown that astronauts could capture objects, work outside, use tools, replace hardware. Now those abilities would eventually be asked to rescue one of the most visible scientific projects ever placed in orbit. But not yet. For now, Hubble remained above Earth, working imperfectly, waiting. The familiar shape was still learning what it could become, and somewhere in the future, the shuttle would have to become an optician. Before that could happen, the missions continued. In October of 1990, Discovery launched on Space Transportation System 41. The crew was Richard Richards, Robert Cabana, William Shepard, Bruce Melnick, and Thomas Akers. The primary payload was Ulysses, a spacecraft designed to study the Sun from an unusual perspective. Most planets orbit the Sun near a common plane. Earth does. Many spacecraft therefore remain relatively close to that broad plane as well. Ulysses was intended to study the Sun's polar regions. To do that, it needed a very different trajectory. The shuttle carried Ulysses into orbit, then an upper stage sent it away. The spacecraft travelled toward Jupiter, not because Jupiter was the final scientific destination, because Jupiter's gravity could bend the spacecraft's path. The giant planet would help send Ulysses into an orbit passing over the Sun's poles. Once again, the shuttle became the first movement in a much longer celestial arrangement. Discovery could not take Ulysses over the poles of the Sun. It did not need to. Its job was to carry the spacecraft to the place where another propulsion system could begin the next part. The enemy here was energy. Changing the plane of an orbit can require enormous amounts of it. A direct attempt to place Ulysses into the desired solar orbit would have been extremely demanding. So the mission used gravity. A planet became part of the trajectory. This is one of the quiet pleasures of orbital mechanics. The obstacles do not always disappear. Sometimes they are rearranged into assistance. Gravity makes leaving Earth difficult. Gravity can also bend a spacecraft toward a destination. The same force can be enemy and tool. It depends on the path. The familiar shape was still learning what it could become. In November, Atlantis launched on Space Transportation System 38. The crew was Richard Covey, Frank Culbertson, Robert Springer, Carl Meade, and Charles Guimard. The mission was dedicated to the United States Department of Defense. Its primary payload was classified. Again, the public story becomes quieter. The shuttle flew. The mission was completed. Atlantis returned. Then came December, Columbia, Space Transportation System 35. The crew was Vance Brand, Guy Gardner, Jeffrey Hoffman, John Lounge, Robert Parker, Samuel Durrance, and Ronald Parise. The mission carried the Astro 1 observatory. The cargo bay became a platform for ultraviolet astronomy. Ultraviolet light reveals a universe different from the one human eyes see. Hot stars, energetic processes, gas between stars, objects whose behavior becomes clearer when observed beyond visible wavelengths, but Earth's atmosphere blocks much ultraviolet radiation. Again, the atmosphere is both protector and obstacle. It shields life from radiation. It also prevents many forms of astronomical observation from the ground. To see more, instruments must rise above much of the air. The shuttle could carry those instruments. It could provide power, pointing, crew support, a temporary orbital platform, and then bring the observatory home. This was different from Hubble. Hubble was designed to remain in orbit. Astro 1 travelled with the shuttle and returned with it. The same cargo bay that could deploy a permanent telescope could also host a temporary observatory. Two models of space science: leave the instrument, or bring it home. The familiar shape was still learning what it could become. The enemy, in this case, was not a broken component. It was the atmosphere itself. The same atmosphere the shuttle needed for landing. This contradiction appears again and again. The atmosphere makes astronomy difficult. The atmosphere makes aerodynamic flight possible. The atmosphere produces dangerous heating during re-entry. The atmosphere eventually allows the orbiter's wings to work. A spacecraft does not move through a universe divided neatly into helpful things and harmful things. The same environment can change roles. The question is when. At orbital speed, the upper atmosphere is a source of heating and drag. Closer to the runway, thicker air becomes the medium that allows the orbiter to glide. The enemy is often not the thing itself. It is the thing encountered under the wrong conditions. The shuttle had to pass through changing conditions without forgetting what it would need next. Heat shield now, wings later, orbital maneuvering engines now, landing gear later. Cargo bay doors open in orbit, cargo bay doors closed before re-entry. The sequence mattered. A correct action at the wrong time could become a problem. That is another enemy. Timing. Spaceflight is full of events that must happen not merely correctly, but correctly at the correct moment. An engine ignition, a separation, a deployment, a rendezvous burn, a door closure, a deorbit burn, a landing gear deployment. Too early can be wrong, too late can be wrong. Sometimes a few seconds matter. Sometimes years of planetary alignment matter. The universe has schedules of its own. The familiar shape was still learning what it could become, and it was learning to arrive on time. The year 1991 began with discovery. Space Transportation System, 39, April. The crew was Michael Coates, Lloyd Hammond, Guillaume Bluford, Gregory Harbour, Richard Heeb, Donald McMonagle, and Charles Veitch. The mission was dedicated to the United States Department of Defense. But unlike some earlier classified flights, several aspects of the mission were publicly discussed. The payloads included experiments related to observing phenomena associated with spacecraft and the space environment. One free-flying payload was deployed and later retrieved. Again, release, separate, observe, rendezvous, retrieve. The sequence had become part of the shuttle's vocabulary, but every rendezvous is an exercise in patience. You do not chase an object in orbit the way one car follows another. You alter your orbit, you wait, you allow the geometry to change, you make another adjustment, distance closes slowly, relative velocity becomes small. The final approach may look gentle. The planning behind it is not. The enemy is relative motion. Two objects can each travel around Earth at thousands of meters per second while appearing almost motionless beside one another. That is the strange calm of rendezvous. Absolute speed is enormous. Relative speed can be nearly zero. The crew looks out the window. The target appears to float. Earth moves beneath both of them. The familiar shape was still learning what it could become, and sometimes becoming precise meant moving slowly while traveling very fast. In June of 1991, Columbia launched on Space Transportation System 40. The mission carried Space Lab Life Sciences 1. The crew was Brian O'Connor, Sidney Gutierrez, James Bargian, Tamara Jernigan, Margaret Seddon, Millie Hughes Fulford, and Drew Gaffney. The focus was life, human life, animal life, the biological effects of spaceflight. The shuttle had carried living research subjects before. Now the mission concentrated more deeply on how bodies respond to weightlessness. On Earth, gravity is so constant that the body develops around it. Bones carry loads, muscles work against weight, fluids distribute themselves under gravity's influence. The balance system uses signals shaped by a world with a reliable down. Remove that familiar condition, and the body adapts. Fluids shift, muscles change, bones respond. The sense of orientation can become confused. The human body is flexible, but flexibility has costs. This made the astronaut both operator and experiment. A crew member could conduct research, while also being part of the phenomenon being studied. The shuttle was not simply carrying humans through space, it was carrying Earth-adapted organisms into an environment where one of Earth's most constant influences had changed. The enemy was not weightlessness itself. Weightlessness made the research possible. The problem was adaptation. The body changes to fit its environment. That is useful while the environment remains changed. But astronauts return to Earth. Gravity returns. The body must adapt again. The shuttle program was therefore studying another kind of transformation. Not rocket to spacecraft, not spacecraft to glider, human body on Earth to human body in orbit, and then back again. The familiar shape was still learning what it could become. Inside it, people were learning the same thing. Later that month, Atlantis launched on Space Transportation System 43. The crew was John Blaha, Michael Baker, Shannon Lucid, James Adamson, and David Lowe. The mission deployed another tracking and data relay satellite. Again, the communications network expanded. Again, an apparently quiet infrastructure mission supported a much larger future. Spaceflight depends on things that are rarely the subject of dramatic posters. Relay satellites, ground antennas, software, tracking, navigation. Data systems. A telescope may make the discovery. A communications network allows the discovery to reach Earth. A crew may perform the experiment. A data system preserves the result. The enemy is not always destruction. Sometimes it is isolation. A spacecraft unable to communicate can be healthy and still be difficult to use. A scientific instrument can collect information that becomes useless if the information cannot be recovered. The universe is full of events. Science requires data, and data requires a path home. The shuttle could carry that path into orbit. The familiar shape was still learning what it could become. In September of 1991, Discovery launched on Space Transportation System 48. The crew was John Creighton, Kenneth Reitler, James Buckley, Charles Gaimar, and Mark Brown. The primary payload was the Upper Atmosphere Research Satellite. The spacecraft was deployed into orbit to study Earth's upper atmosphere, chemistry, energy, the processes affecting ozone, the interactions occurring far above the surface. Again, the shuttle looked down toward the planet it had left. There is a tendency to imagine space science as a study of distant things, stars, galaxies, planets, but orbit is also an extraordinary place from which to study Earth. The atmosphere has layers. Processes occurring high above the ground can affect conditions below. Satellites can observe globally, repeatedly, across regions difficult to study from one location. The shuttle could deploy an instrument and leave it there to continue working. The mission ended. The satellite's mission continued. This pattern had become familiar. The orbiter was temporary. The consequences could last for years. Then came November. Atlantis, Space Transportation System, 44. The crew was Frederick Gregory, Terence Henricks, Story Musgrave, Mario Runco, James Voss, and Thomas Hennon. The mission was dedicated to the United States Department of Defense. It deployed a Defense Support Program satellite. The mission ended earlier than originally planned because of an inertial measurement unit problem. This is another form of the enemy. Redundancy can protect a spacecraft. Multiple systems can provide backups. But redundancy is not infinity. If a component fails, mission planners must consider what remains. What happens if another fails? How much margin is left? Can the mission continue safely? Sometimes the correct answer is to come home early. A shortened mission is not necessarily a failed mission. It can be evidence that the system recognizes a changing boundary. This is an important distinction. Success is not always completing every planned day. Sometimes success is respecting the remaining margin. The familiar shape was still learning what it could become, and sometimes it had to become a spacecraft willing to stop. The year 1992 opened with Discovery, Space Transportation System. 42, January. The crew was Ronald Grubb, Stephen Oswald, Norman Thagard, David Hilmers, William Reddy, Roberta Bondar, and Ulf Merbold. The mission carried the International Microgravity Laboratory 1. The name tells us something about the changing character of shuttle science. International. Researchers and crew members from different countries contributed to a laboratory in orbit. Microgravity. The environment itself was part of the instrument. Laboratory. The shuttle had become a place where controlled scientific work could happen. Experiments studied materials, life sciences, fluid behavior, processes that gravity can mask or dominate on Earth. The enemy here was disturbance. A microgravity experiment does not take place in perfect stillness. Crew members move, equipment operates, thrusters fire, machines vibrate. The spacecraft experiences small accelerations. For some experiments, these disturbances matter. The absence of ordinary weight does not create perfect nothingness. It creates a different environment that still has to be measured and understood. Even quiet has structure. Even floating has forces. The familiar shape was still learning what it could become. In March, Atlantis launched on Space Transportation System 45. The crew was Charles Bolden, Brian Duffy, Catherine Sullivan, David Leesmer, Michael Foale, Dirk Frimout, and Byron Lichtenberg. The mission carried the first atmospheric laboratory for applications in science. The shuttle became an observatory for Earth's atmosphere. The crew studied interactions involving the atmosphere and the sun. Once again, the atmosphere was not simply something the shuttle passed through, it was a subject. A spacecraft launched through the atmosphere in order to study the atmosphere from above, then returned through the atmosphere it had studied. There is something quietly circular about that. The vehicle escaped the lower layers only temporarily. It looked back, measured, observed, then entered again. The enemy and the object of study were sometimes the same thing, not because the atmosphere was hostile, because context changes meaning. Air in the lungs is life. Air compressed ahead of an orbiter at re-entry speed becomes heat. Air between a telescope and the stars can blur observations. Air in the upper atmosphere becomes a scientific record of solar influence and chemical change. The universe does not label things for us: useful, dangerous, beautiful, inconvenient. Those are relationships. The familiar shape was still learning what it could become, and the meaning of the environment changed with it. Later in March, Atlantis landed. Then came May. Endeavour, a new orbiter, Space Transportation System. 49, the first flight of Endeavour. The shuttle fleet had lost Challenger. Now a new vehicle entered service. Its name had been chosen through a national competition involving students. Endeavour was named for a ship associated with exploration, but its first mission would not be a gentle introduction. The target was Intelsat 6, a communications satellite that had failed to reach its intended orbit after launch on another rocket in 1990. The satellite remained in a low orbit. A new propulsion stage needed to be attached so it could continue toward its proper destination. The mission was a rescue, but not in the dramatic sense of saving people. It was an attempt to recover the usefulness of a machine. Endeavour approached the satellite. Astronauts went outside. The initial attempts to capture Intelsat 6 did not succeed. The satellite was difficult to grasp. The planned method was not working. This is where the enemy becomes improvisation's reason for existing. A plan can be excellent. Reality can still refuse to cooperate. The crew and ground teams developed another approach. 3 astronauts would perform a spacewalk together. Pierre Thuot, Richard Heeb, Thomas Akers. 3 people outside the shuttle at the same time. They positioned themselves around the satellite, and together, by hand, they captured it. A communications satellite weighing several thousand kilograms, weightless in orbit, not massless. The astronauts had to control it carefully. They attached the new propulsion stage. The satellite was released. Its journey continued. The mission had required an unplanned method. The shuttle had become a place where people could adapt. That may be one of the most important capabilities the program ever carried. Not a piece of hardware. Human judgment at the destination. A robotic spacecraft can perform extraordinary tasks, but it generally performs tasks anticipated in advance. A human crew can encounter a problem, look at it, discuss it, change the plan, use hands, use tools, try something different. This flexibility is expensive. Humans require life support, protection, training, return capability. But when the unexpected appears, people can become part of the solution. The familiar shape was still learning what it could become. And on Endeavour's first mission, it became a place for improvisation. The mission also included experiments related to future space station construction. Astronauts worked outside for extended periods. They tested methods, tools, techniques. Again, the future was being rehearsed. A permanent station would require assembly, maintenance, repeated spacewalks. The shuttle was slowly learning how to support that work. But every successful improvisation contains a warning. You cannot plan to improvise your way out of everything. Human ingenuity is not a substitute for safe design. A crew may solve one unexpected problem, another may offer no time. The enemy remains uncertainty, and uncertainty does not promise to arrive in a convenient form. In June of 1992, Columbia launched on Space Transportation System 50. The crew was Richard Richards, Kenneth Bowersox, Bonnie Dunbar, Ellen Baker, Carl Mead, Lawrence DeLucas, and Eugene Trin. The mission carried the United States Microgravity Laboratory 1. Columbia remained in orbit for almost 14 days. At the time, it was the longest shuttle mission yet. Duration was becoming another frontier. The early shuttle flights had lasted only a few days. Now missions were stretching longer. A longer mission means more time for science, more observations, more experiments, but it also means more consumables, more food, more water, more waste, more crew time, more exposure to the space environment, more opportunities for equipment to fail. Time is not empty. A longer mission carries weight even when the spacecraft's mass does not change. The familiar shape was still learning what it could become. Now, it was learning how long it could remain that way. The laboratory operated in orbit. Experiments examined materials and physical processes in microgravity. The mission continued, day after day, orbit after orbit, sunrise, sunset, sunrise again. The shuttle was becoming less like a brief visitor, not yet a space station, but something closer to a temporary home. Then came July, Atlantis, Space Transportation System 46. The crew was Lauren Shriver, Andrew Allen, Jeffrey Hoffman, Franklin Chang Diaz, Claude Nicollier, Marcia Evans, and Franco Malerba. The mission carried two major payloads, the European Retrievable Carrier and the Tethered Satellite System. The European Retrievable Carrier was deployed successfully. It would remain in orbit and later be retrieved by another shuttle mission. Again, the program created a task stretched across time: deploy now, return later. The Tethered Satellite System was more complicated. The idea involved deploying a satellite on a long tether from the shuttle. The system was intended to study the behavior and physics of a tethered spacecraft in orbit. But the satellite did not deploy to the intended distance. The experiment encountered problems. It did not achieve all of its objectives. This is the enemy in another form: novelty. The first time a complicated system is used in its real environment, the environment may reveal things that testing did not. A mechanism can behave differently. A line can jam. Friction can appear where it was not expected. Materials can interact in ways that become important only under actual conditions. Engineering tries to predict. Testing tries to discover. But reality receives the final vote. The tether experiment would return on a later mission. The familiar shape was still learning what it could become. And sometimes, learning meant trying again. In September of 1992, Endeavour launched on Space Transportation System 47. The crew was Robert Gibson, Curtis Brown, Mark Lee, Jerome Apt, Jan Davis, Mae Jemison, and Mamoru Mori. Mae Jemison became the first black woman to travel into space. The mission carried Spacelab J. The letter J referred to Japan. The laboratory conducted experiments in life sciences and materials processing. Again, international research. Again, the shuttle as a laboratory. Again, human bodies and physical materials placed into an environment where gravity's ordinary influence was reduced. The crew itself represented another widening of who participated in the program. The shuttle had become a vehicle through which scientists, physicians, engineers, and international partners could enter orbit. But human diversity did not remove human limits. Every person aboard still needed sleep, food, air, space. Every person had to train. Every experiment competed for time. The schedule inside a shuttle mission could be dense. A spacecraft may float in apparent silence above Earth. Inside, there is work, checklists, experiments, communications, meals squeezed between tasks, equipment that behaves unexpectedly, objects that drift away from where someone was certain they had placed them. Weightlessness can turn housekeeping into orbital archaeology. The familiar shape was still learning what it could become, and humans were still learning where the pen had floated. In October, Columbia launched on Space Transportation System 52. The crew was James Weatherby, Michael Baker, Charles Veach, William Shepard, Tamara Jernigan, and Stephen McLean. The mission deployed the Laser Geodynamics Satellite 2. It also carried the United States Microgravity Payload 1. One mission, a satellite deployment, a scientific payload platform, different objectives sharing the same flight. This was another expression of efficiency. If the shuttle had available capacity, multiple investigations could travel together, but combining objectives creates integration work. One payload must not interfere with another. Power requirements must be managed. Crew time must be scheduled. The orbit must serve the mission. The spacecraft becomes a shared environment, and shared environments require compromise. The enemy is sometimes competition between good ideas. There may be more useful experiments than time, more payloads than mass capacity, more observations than the mission can perform. Spaceflight does not choose between good and bad. Often, it chooses between good and also good. Constraint becomes priority. Then, in December of 1992, Discovery launched on Space Transportation System 53. The crew was David Walker, Robert Cabana, Guillaume Bluford, James Voss, and Michael Clifford. The mission was dedicated to the United States Department of Defense. It deployed a classified payload. It would become the final shuttle mission devoted entirely to the Department of Defense. An era within the larger program was ending. The shuttle had spent years carrying national security payloads. Now that role was changing. The spacecraft would continue to carry a wide variety of missions, but the balance was shifting. Scientific research, Earth observation, telescope servicing, international cooperation, and eventually, space station construction. The familiar shape was still learning what it could become, and sometimes, becoming something new means slowly ceasing to be something else. The calendar turned to 1993. The shuttle program had now accumulated more than 50 missions. The experimental flights of the early 1980s were becoming distant. The fleet had launched planetary probes, laboratories, communications satellites, classified payloads, Earth-observing satellites, astronomical instruments. It had retrieved spacecraft, repaired spacecraft, carried international crews, supported increasingly long missions. But above Earth, Hubble was still waiting. Its flawed primary mirror had not changed. The telescope continued to produce science. Engineers and scientists had developed a solution. The mirror itself would not be replaced. Instead, new optical hardware would compensate for the error. It was a remarkable idea. The telescope had the wrong optical shape, so the correction would be built around the flaw. The solution would not erase the mistake. It would understand the mistake precisely enough to counteract it. But before astronauts could perform that repair, the shuttle program still had several missions to fly, and every one of them would continue the same quiet argument with the enemy. In January of 1993, Endeavour launched on Space Transportation System 54. The crew was John Casper, Donald McMonagle, Mario Runco, Gregory Harbour, and Susan Helms. The mission deployed a tracking and delta relay satellite, another piece of communications infrastructure, another machine placed into orbit so that other machines could speak more reliably with Earth. The mission also included a spacewalk. Astronauts tested their ability to move and work in preparation for future tasks. Space station assembly was approaching. Hubble servicing was approaching. The ability to work outside the shuttle was no longer a special curiosity. It was becoming central to the future. The enemy outside was simple to describe. Vacuum, extreme temperatures, radiation, no breathable air, no pressure suitable for the human body. But the spacesuit turned that environment into a workplace. A very small spacecraft worn around one person. Life support, pressure, cooling, communications, mobility, protection. The astronaut carried an environment into the environment. The familiar shape was still learning what it could become, and outside it, humans carried smaller spacecraft around themselves. In April, Discovery launched on Space Transportation System 56. The crew was Kenneth Cameron, Stephen Oswald, Michael Fowle, Kenneth Cockrell, and Ellen Ochoa. Ellen Ochoa became the first Hispanic woman to travel into space. The mission carried the second atmospheric laboratory for applications in science. The crew studied Earth's atmosphere and its interaction with solar energy. The shuttle again became an atmospheric observatory. The mission also used a shuttle-pointed autonomous research tool for astronomy. An instrument was deployed and later retrieved. Again, the pattern: release, observe, return. The cargo bay was not simply storage. It was the center of a temporary ecosystem of machines. Some stayed attached, some flew free, some came back, some did not. The shuttle could create a small neighborhood in orbit, but neighborhoods require traffic control. Every free-flying object has a trajectory. Every deployment must avoid collision. Every retrieval must be planned. The enemy is proximity without control. Space appears vast, near a spacecraft. A few meters can matter. In June, Endeavour launched on Space Transportation System 57. The crew was Ronald Grabe, Brian Duffy, David Lowe, Nancy Sherlock, Peter Wisoff, and Janice Voss. The mission carried the European retrievable carrier that had been deployed during Space Transportation System 46. Now, nearly a year later, Endeavour went to retrieve it. The robotic arm captured the platform. The cargo returned to Earth. Again. One shuttle mission completed work begun by another. The program was becoming a chain of revisits. The mission also carried SpaceHab for the first time. SpaceHab was a pressurized module that expanded the usable working volume available to the crew. The shuttle's interior could be enlarged without redesigning the orbiter itself. Place a module in the cargo bay, connect it, create more room for experiments and work. This is perhaps the clearest answer yet to our central question. How did the same spacecraft idea keep becoming a completely different machine, without ever changing its basic shape? By allowing new spaces to exist inside the old boundary. The orbiter did not become physically unrecognizable. Its usable interior changed, its payload changed, its purpose changed. A module could turn cargo volume into human working volume. A telescope could turn the bay into a launch cradle. A satellite could turn it into a delivery vehicle. A captured spacecraft could turn it into a return container. The exterior shape was only the envelope. The mission lived inside. The familiar shape was still learning what it could become. Then came July, Columbia, Space Transportation System 58. No, not yet. First came Space Transportation System 51, Discovery. September of 1993. The crew was Frank Culbertson, William Reddy, James Newman, Daniel Bursch, and Carl Waltz. The mission deployed the Advanced Communications Technology satellite. It also deployed and retrieved the Shuttle Pallet satellite carrying the orbiting and retrievable far and extreme ultraviolet spectrometer. The names were becoming long, the missions were becoming layered. Communications technology, ultraviolet astronomy, deployment, retrieval, multiple objectives. The shuttle was becoming a platform where different fields briefly shared the same journey. Then, in October, Columbia launched on Space Transportation System 58. The crew was John Blaha, Richard Searfoss, Margaret Seddon, William MacArthur, David Wolfe, Shannon Lucid, and Martin Fettman. The mission carried Spacelab Life Sciences 2. For 14 days, the crew studied how living systems responded to spaceflight: humans, animals, physiology, adaptation. The mission continued the work of understanding what happens to bodies when gravity no longer loads them in the familiar way. This research mattered beyond the shuttle. If humans were ever to remain in space for longer periods, the body itself would become one of the central engineering problems. A spacecraft can be repaired. A human body must repair itself. Exercise can help. Countermeasures can help. Medical monitoring can help. But biology is not a machine with replaceable modules. The enemy is adaptation itself. The body is excellent at adjusting to the environment it inhabits. In space, that adjustment can make returning to gravity more difficult. The same flexibility that keeps an organism alive can create new problems. The familiar shape was still learning what it could become. Inside it, the human body was doing the same. Then came December of 1993, Endeavour, Space Transportation System 61. The first servicing mission to the Hubble Space Telescope. The crew was Richard Covey, Kenneth Bowersox, Story Musgrave, Catherine Thornton, Claude Nicollier, Jeffrey Hoffman, and Thomas Akers. Hubble was waiting. The telescope had been in orbit for more than 3 years. Its primary mirror could not be reshaped in space, but engineers had designed corrective optics. One instrument would be replaced with a system called the Corrective Optics Space Telescope Axial Replacement. Another new camera had its own corrective optics. The solution was almost beautifully strange. A telescope had been given the wrong prescription, so astronauts were going to bring it glasses. Endeavour approached Hubble. Claude Nicollier used the robotic arm to capture the telescope. The observatory was secured in the cargo bay. Then the spacewalks began. 5 of them. Astronauts worked outside for hours. They replaced equipment, installed new hardware, changed solar arrays, serviced the telescope. The mission demanded choreography, tools, restraints, training, patience. The astronauts had rehearsed the work underwater. They had practiced procedures. They had studied the telescope, but the real Hubble was now in the cargo bay. The real hardware had been exposed to space. The real fasteners had to move. The real components had to fit. The enemy was no longer an abstract flaw in a mirror. It was every small difficulty between the plan and the completed repair. A stubborn connector, a component that must be handled carefully, a tool that must remain controlled, a spacesuit glove between a human hand and the object being touched. Time, fatigue, the limits of the robotic arm, the geometry of the cargo bay, the need to protect the telescope while working on it. Yet the work continued, one task, then another. The corrective hardware was installed, the telescope was released, and later, the first corrected images arrived. The repair had worked. Hubble could see sharply. The shuttle had become something it had never been before, a repair ship for an observatory, a platform from which humans could correct a manufacturing error in a telescope hundreds of kilometers above Earth. This was the elegant answer hidden inside years of earlier missions, the first untethered spacewalks, the first satellite capture, the solar maximum mission repair, the retrieval of stranded satellites, the experiments with tools, the robotic arm, the repeated practice of rendezvous, the spacewalk training, the ability to carry large replacement hardware. None of those earlier missions was the Hubble servicing mission, but all of them helped create the world in which the Hubble servicing mission was possible. The familiar shape was still learning what it could become, and now, for a moment, it had become a pair of hands for a telescope. This brings us back to the enemy. The mirror flaw had already happened. It could not be wished away. The solution came from accepting the error precisely, measure it, understand it, design around it, carry the correction into orbit, install it. The enemy was not defeated by pretending the telescope was perfect. It was defeated by knowing exactly how it was imperfect. That may be one of the deepest patterns in engineering. Reality does not require perfection. It requires accurate understanding. A flawed system that is understood can sometimes be corrected. A flawed system that is misunderstood remains dangerous. The shuttle itself was no exception. Its enemies were not only gravity and heat, they were gaps between reality and belief. The distance between what a component was assumed to do and what it actually did. The distance between damage that appeared acceptable and damage that was not. The distance between a schedule and the physical conditions on the launch pad. The distance between a plan and the object waiting in orbit. Every mission tried to close those distances. Testing, measurement, inspection, training, redundancy, review, and sometimes improvisation. But the enemy never disappeared, because uncertainty cannot be removed completely. A spacecraft is built before it flies. The real environment arrives later. A mission is planned before it happens. The unexpected arrives during it. The familiar shape was still learning what it could become. And perhaps that is why the shuttle's greatest strength and greatest vulnerability were so closely related. It was complicated because it could do many things. It could do many things because it was complicated. The cargo bay created possibilities. The thermal protection system allowed return. The wings allowed runway landing, the crew allowed adaptation, the robotic arm allowed interaction, the airlock allowed work outside, the main engines helped provide the performance needed for orbit, the solid rocket boosters provided enormous thrust, the external tank carried propellants for the main engines. Remove enough complexity, and the shuttle stops being the shuttle. Keep the complexity, and every mission must manage it. There was no simple version of the same machine waiting underneath. The enemy could not be removed by making one improvement. It had to be managed continuously, mission after mission, inspection after inspection, decision after decision. And the program was about to enter a new period. The shuttle had learned how to repair a great observatory. Soon, it would begin learning how to visit something much larger, not a satellite, not a telescope, a place where people were already living. A Russian space station called Mir. The Cold War was ending. Old rivals were becoming partners. Docking systems would have to work. Procedures would have to align. Languages would meet. Hardware built under different engineering traditions would have to connect in orbit. The shuttle would have to become a ferry, a bridge, a visiting spacecraft, and eventually a rehearsal for something larger still, the International Space Station. But before the elegant solution can fully appear, we should remember what has been working against it all along: distance, mass, heat, cold, vacuum, radiation, wear, time, uncertainty, complexity, and the quiet human habit of becoming comfortable with what happened to work yesterday. The enemy was never one thing. That would have been easier. The familiar shape was still learning what it could become. Now, we can begin to see the solution. Not a perfect machine. Not a machine without limits. Something more interesting. A machine built to meet other machines. A machine whose greatest ability was not simply flying, it was connecting. Let us go find it. A machine built to meet other machines. That was the solution. Not a spacecraft that could do everything alone. Not a vehicle that could travel everywhere. Not a permanent laboratory. Not a permanent home. Not a telescope. Not a satellite. Not a space station. Something stranger. A spacecraft that could arrive carrying the missing piece. A person, a tool, an instrument, a replacement part, a laboratory, a docking system, a satellite, a section of structure. The shuttle did not need to become every machine. It needed to reach them, and once it arrived, it needed to connect. The familiar shape was still learning what it could become. By the beginning of 1994, the shuttle had already demonstrated almost every ingredient of this idea. It had deployed satellites, retrieved satellites, repaired satellites, carried laboratories, launched planetary spacecraft, released free-flying instruments, captured them again, returned large objects to Earth, supported long spacewalks, carried international crews, serviced the Hubble Space Telescope. Each achievement had looked like a separate mission. Now, slowly, the pattern was becoming visible. The shuttle's greatest ability was not one piece of hardware. It was the ability to create temporary relationships. Earth and orbit, astronaut and satellite, telescope and replacement instrument, laboratory and researcher. One mission and another mission years later. One country and another. The cargo bay was where those relationships were carried. The robotic arm was how some of them were reached. The airlock was how people crossed from inside to outside. The orbital maneuvering system was how the shuttle approached. The wings were how people and hardware returned. The solution was not simplicity, it was connection. And in 1994, that solution began to widen. Let us begin. The first shuttle mission of the year was Space Transportation System 60. Discovery launched in February. The crew was Charles Bolden, Kenneth Reitler, Jan Davis, Ronald Sager, Franklin Chang Diaz, and Sergei Krikalev. Sergei Krikalev was a Russian cosmonaut. His presence aboard Discovery was historic. He became the first Russian cosmonaut to fly aboard the American Space Shuttle. Only a few years earlier, the United States and the Soviet Union had been geopolitical rivals. The Soviet Union had dissolved in 1991. Now, a Russian cosmonaut was sitting inside an American spacecraft. The change was larger than one seat on one flight. Spaceflight had always contained international cooperation, but the relationship between the American and Russian human spaceflight programs was entering a new phase. Different spacecraft, different languages, different procedures, different histories, different engineering traditions. And now, increasingly, shared missions. Discovery carried a payload called the Wake Shield Facility. It was a free-flying platform designed to create an unusually clean vacuum environment in its wake as it moved through the thin traces of atmosphere remaining in low Earth orbit. The platform was deployed using the robotic arm. It flew separately, then it was retrieved. Again, release, separate, work, return. The sequence was familiar now, but familiarity should not hide the precision. A free-flying spacecraft had to be placed into the correct relative motion. The shuttle had to move away. The two vehicles had to remain within a planned relationship. Later, they had to meet again. The shuttle was becoming comfortable with temporary separation. This is an important part of connection. To connect well, a spacecraft must also know how to let go. The familiar shape was still learning what it could become, and now, one of the people inside it represented a future connection much larger than the free-flying platform outside. Sergei Krikalev had already lived aboard the Russian space station Mir. Soon, American astronauts would do the same. Soon. The shuttle itself would approach Mir, but first, there was more to learn. In March of 1994, Columbia launched on Space Transportation System 62. The crew was John Casper, Andrew Allen, Pierre Thuot, Charles Gaimard, and Marcia Ivins. The mission carried the United States Microgravity Payload 2 and experiments associated with the Office of Aeronautics and Space Technology. Columbia remained in orbit for almost 14 days. Again, duration, again, science, again. The shuttle as a temporary laboratory. But the longer missions were quietly teaching the program how to manage people and systems over extended periods. A future involving space stations would require something different from brief visits. People would remain in orbit for months. The shuttle itself could not support that indefinitely. Its consumables were finite, its power system depended on fuel cells, its mission duration had limits. But the shuttle could carry people to a place designed for longer stays. This is where the elegant solution becomes clearer. Do not make the shuttle a permanent space station. Make it capable of reaching one. The familiar shape was still learning what it could become. A temporary spacecraft can support permanence by visiting it. In April, Endeavour launched on Space Transportation System 59. The crew was Sidney Gutierrez, Kevin Chilton, Linda Godwin, Jerome Apt, Michael Clifford, and Thomas Jones. The mission carried the Space Radar Laboratory 1. The cargo bay became an Earth observing platform. Radar instruments examined the planet, land surfaces, geological structures, vegetation, environmental processes. The shuttle flew with its cargo bay oriented toward Earth for much of the scientific work. Once again, the same vehicle changed its relationship with the planet below. A launch vehicle points away from Earth. An Earth observing platform looks back. A returning glider aims toward a runway. The physical orientation of the orbiter changed with the task. So did the meaning of the spacecraft. The radar laboratory was not permanent. It traveled with Endeavour. It worked. It returned. Months later, a similar mission would fly again. Repeat observation matters. A single image can show a place. Repeated images can show change. The shuttle could carry instruments back to orbit and observe again under different conditions. The solution was not always to leave a satellite permanently in space. Sometimes, it was to bring the laboratory home, improve understanding, and fly again. The familiar shape was still learning what it could become. In July, Columbia launched on Space Transportation System 65. The crew was Robert Cabana, James Halsell, Richard Heeb, Carl Walls, Leroy Chiao, Donald Thomas, and Chiaki Mukai. The mission carried the second International Microgravity Laboratory. For more than 2 weeks, Columbia became a scientific workplace. At the time, it was the longest shuttle mission yet. The laboratory studied life sciences, materials, fluid physics, processes influenced by the microgravity environment. Chiaki Mukai became the first Japanese woman to travel into space. Again, the crew reflected the international nature of the research. A spacecraft designed in one country could become a laboratory for experiments involving many. The shuttle was not becoming less American, it was becoming more connected. That distinction matters. Connection does not require everything to become the same. Different institutions can remain different. Different countries can maintain their own programs. Different machines can preserve their own designs. The challenge is creating an interface, a place where the differences can meet. This principle was already visible in hardware. A payload does not need to be part of the orbiter forever. It needs compatible attachment points, power, data, mechanical support. A satellite does not need to become the shuttle. It needs a deployment system. A telescope does not need to be redesigned as an orbiter. It needs to be reachable and serviceable. The elegant solution was the interface. The familiar shape was still learning what it could become. And soon, the most important interface would be a docking mechanism. In September of 1994, Discovery launched on Space Transportation System 64. The crew was Richard Richards, Blaine Hammond, Jerry Linenger, Susan Helms, Carl Mead, and Mark Lee. The mission carried another flight of the LiDAR in Space technology experiment. A laser-based instrument studied Earth's atmosphere. The mission also deployed and retrieved the shuttle-pointed autonomous research tool for astronomy. Again, a free-flying platform. Again, the shuttle created temporary distance and then closed it. But Space Transportation System 64 also included a spacewalk by Mark Lee and Carl Mead. They tested a device called the Simplified Aid for Extravehicular Activity Rescue, a small propulsion system designed for emergency use by an astronaut outside a spacecraft. The device could help an astronaut return if separated from the vehicle. This was not the same as the earlier manned maneuvering unit. The purpose was different. The manned maneuvering unit had been designed for planned free flight. The newer device was a rescue system, a last means of self-return. The problem was separation. The solution was a small amount of independent mobility. Again, connection. Even safety could be understood through it. A person outside the spacecraft needed a reliable relationship with the vehicle. Tethers, handrails, foot restraints, procedures. And if those failed, a way to cross the distance back. The familiar shape was still learning what it could become, and every connection had to consider what happened if the connection was lost. Then came September again. Endeavour launched on Space Transportation System 68, the second Space Radar Laboratory mission. The crew was Michael Baker, Terence Wilcutt, Thomas Jones, Stephen Smith, Daniel Bursch, and Peter Wisoff. The instruments returned to study Earth. This time, the value was partly in repetition. The planet had changed, conditions had changed, the observing geometry had changed. The same regions could be examined again. Science often advances through return. Observe once, observe again, compare. The shuttle program itself was becoming a system of return. Return to orbit, return to a satellite, return to a telescope, return to an experiment, return to a scientific question with better tools. Reuse was not merely the reuse of the orbiter. It was the reuse of access, the ability to come back. That may be the deeper meaning of a reusable spacecraft. Not that the same machine flies twice. That the same destination can become reachable again. The familiar shape was still learning what it could become, and soon the destination would be inhabited. In November of 1994, Atlantis launched on Space Transportation System 66. The crew was Donald McMonagle, Curtis Brown, Ellen Ochoa, Joseph Tanner, Jean-Francois Clairvoy, and Scott Parazinski. The mission carried the third atmospheric laboratory for applications and science. Again, The shuttle studied Earth's atmosphere. Again, international participation. Again, a temporary laboratory. But the program was now moving toward a major transition. The next year would bring the shuttle and Mir closer together. The idea required more than political agreement. Spacecraft do not dock through goodwill. Hardware must align. Speeds must match. Pressures must be managed. Structures must tolerate loads. Guidance systems must bring two large vehicles together without collision. Communications must work. Procedures must be understood by crews and controllers on both sides. Emergency situations must be considered. The docking mechanism itself must fit. This is the elegance of an interface. A small region of hardware can connect two enormous systems. The spacecraft do not need to be identical. They need to agree at the boundary. The familiar shape was still learning what it could become. And now, the boundary was approaching. The year 1995 began with Discovery, Space Transportation System 63, February. The crew was James Weatherby, Eileen Collins, Bernard Harris, Michael Foale, Janice Voss, and Vladimir Titov. Eileen Collins became the first woman to pilot a space shuttle. Vladimir Titov was a Russian cosmonaut. The mission's most important objective was a rendezvous with Mir, not docking, not yet. Approach. Discovery flew close to the Russian space station. The two spacecraft came within roughly 11 meters of one another. 11 meters, after traveling around Earth at orbital velocity, after launching from different places, after being built by different nations. The final distance was small enough to fit inside an ordinary room, but those 11 meters represented years of history. The shuttle approached Mir slowly, carefully. The crews could see one another's spacecraft. The mission tested techniques and operations that would support future docking flights. This was the rehearsal. A near meeting before the meeting. The familiar shape was still learning what it could become. And now, it had become a visitor standing just outside the door. The mission also included a spacewalk by Bernard Harris and Michael Foale. Bernard Harris became the first black astronaut to perform a spacewalk. The astronauts tested the effects of cold on their spacesuits and equipment. Again, the environment. Again, the body protected by a wearable spacecraft. Again, a mission combining several purposes. Rendezvous, international cooperation, spacewalk research, operations. The shuttle was becoming a bridge before the bridge physically connected. This is how large changes often begin, not with the final event, with rehearsal, approach, measurement, learning the geometry, learning how the other vehicle appears through the window, learning how communications flow, learning how close is close. Then, in March of 1995, Endeavour launched on Space Transportation System 67. The crew was Stephen Oswald, William Gregory, Tamara Jernigan, John Grunsfeld, Wendy Lawrence, Samuel Durrance, and Ronald Parise. The mission carried Astro 2. Again, ultraviolet astronomy. Again, the shuttle as an observatory. The instruments studied stars, galaxies, and other astronomical targets in wavelengths largely blocked by Earth's atmosphere. The mission lasted more than 16 days. Another duration record for the shuttle at the time. The orbiter remained in space. The instruments worked. The crew worked in shifts. The temporary observatory stayed alive through repeated orbits. This mission may seem separate from the approaching Mir story, but it belongs to the same solution. The shuttle did not need one permanent identity. Its value came from changing configuration. 1 month, approaching a space station. The next, becoming an ultraviolet observatory. A permanent space station is excellent at remaining in space. A dedicated telescope is excellent at observing. The shuttle's specialty was different. It could arrive configured for the work of that particular mission. The familiar shape was still learning what it could become, and its elegance came from refusing to become only one thing. In June of 1995, Discovery launched on Space Transportation System 70. The crew was Terence Henricks, Kevin Kriegel, Nancy Curry, Donald Thomas, Mary Ellen Webber, and Albert Sacco. The mission carried the tracking and data relay satellite G, another communications satellite, another piece of infrastructure, another reminder that connection is not only physical. Spacecraft connect through radio, data, voice, commands. A docking mechanism joins structures. A communications network joins information. Both are interfaces. Both can determine whether distant systems function as one larger system. The shuttle deployed the satellite. The network expanded. The mission returned. Then, later that month, Atlantis stood ready for one of the most important flights in the entire program, Space Transportation System 71, the first shuttle mission to dock with Mir. The crew was Robert Gibson, Charles Precourt, Ellen Baker, Gregory Harbour, Bonnie Dunbar, Anatoly Soloviev, and Nikolai Budarin. But the crew list alone does not tell the full story. When Atlantis returned, the people aboard would be different. That was part of the mission. The shuttle was about to become a ferry between Earth and a space station. Norman Thagard, an American astronaut, had already traveled to Mir aboard a Russian Soyuz spacecraft. He had been living aboard the station. Atlantis would bring him home. At the same time, Soloviev and Budarin would remain aboard Mir. People would exchange places. The spacecraft would not merely connect hardware, it would connect human journeys. Atlantis launched on June 27, 1995. It approached Mir. The two spacecraft moved around Earth. The distance closed. Kilometers became hundreds of meters. Hundreds became tens. Relative motion became careful, slow, deliberate. The shuttle was large, Mir was large. Neither object was resting. Both were falling around Earth together. The final approach required precision. The docking system aligned. The vehicles connected. For the first time, a space shuttle had docked with Mir. Two spacecraft became one temporary complex. American hardware, Russian hardware, different histories, different designs, connected at one boundary. This is the elegant solution in its clearest form. The machines did not need to become identical. They needed an interface that worked. The familiar shape was still learning what it could become, and now it had become a doorway. Hatches opened. People moved between the spacecraft. For several days, Atlantis and Mir remained joined. The combined complex was larger than either spacecraft alone. The shuttle had arrived with one set of capabilities. Mir had another. The station could support long-duration habitation. The shuttle could carry people and substantial cargo between Earth and orbit. One vehicle was designed to remain. The other was designed to return. Together, temporarily, they formed a system neither could create alone. This is the answer to the central question. How did the same spacecraft idea keep becoming a completely different machine, without ever changing its basic shape? By changing what it connected to. A shuttle alone was one spacecraft. A shuttle holding Hubble in its cargo bay became a servicing platform. A shuttle carrying Spacelab became a laboratory. A shuttle releasing Galileo became a planetary launch platform. A shuttle docked to Mir became part of a space station. The orbiter did not need to change its entire exterior. The relationship changed, and relationships can transform machines. The familiar shape was still learning what it could become. Norman Thagard transferred to Atlantis for the journey home. He had spent more than 100 days in space. His mission represented a new kind of American long-duration spaceflight. The shuttle had not supported those months alone. Mir had. Now Atlantis provided the return. This was the division of labor. A station for staying, a shuttle for coming and going. The solution appears simple after it works. It was not simple. Docking required hardware, training, joint procedures, international coordination, mission planning, language, trust, the ability to understand another program's way of doing things. The physical docking mechanism was only the visible interface. Behind it were human interfaces, engineers speaking with engineers, controllers speaking with controllers, astronauts training with cosmonauts, documents translated, procedures compared, different assumptions discovered. A connector between spacecraft may be made of metal. A partnership is made of repeated understanding. The familiar shape was still learning what it could become. And now, the people around it were learning the same thing. Atlantis undocked from Mir. The vehicles separated. The shuttle returned to Earth. Mir remained in orbit. This is another elegant feature of a temporary connection. It does not need to last forever to matter. Dock, transfer, work, separate, return. The shuttle could connect without becoming permanently attached. The station could remain a station. The shuttle could remain a shuttle. Each preserved its own role. The interface allowed cooperation without erasing difference. That principle would become central to the International Space Station. Modules built by different countries, launched at different times, connected in orbit, a station assembled from interfaces, but that future was still forming. For now, Mir was the classroom, the shuttle was the student, and sometimes the teacher. The familiar shape was still learning what it could become. In July of 1995, Discovery launched on Space Transportation System 70. No, that mission had already flown. The chronology now moves to Space Transportation System 69, Endeavour, September of 1995. The crew was David Walker, Kenneth Cockrell, James Voss, James Newman, and Michael Gernhardt. The mission deployed and retrieved the wake shield facility for another flight. Again, a free-flying platform. Again, separation and reunion. The mission also included a spacewalk. Astronauts tested tools and techniques for future International Space Station assembly. The future station did not yet exist in orbit, but its construction methods were already being rehearsed. This is how enormous machines begin, not with the final structure, with small questions. Can this tool be used while wearing gloves? Can this restraint hold an astronaut in the correct position? Can this object be moved safely? How long does the task take? What happens when a large structure begins to move? How should a crew member translate along the exterior? The grand future is built from ordinary details. A space station may be visible from the ground as a bright moving point. Its construction depends on bolts, connectors, handrails, cables, procedures. The familiar shape was still learning what it could become, and now it was learning how to become a builder. In October, Columbia launched on Space Transportation System 73. The crew was Kenneth Bowersox, Kent Rominger, Catherine Thornton, Catherine Coleman, Michael Lopez Alegria, Fred Leslie, and Albert Sacco. The mission carried the second United States microgravity laboratory for more than 15 days. Columbia became a laboratory. Again, the contrast. One shuttle mission docked with Mir. Another tested construction techniques. Now another became a microgravity research platform. The fleet moved between identities. The solution was modularity. Not perfect modularity, not unlimited modularity, but enough. A cargo bay that could accept different payload arrangements. A crew system that could support different specialists. A flight plan that could be built around different objectives. A spacecraft that could rendezvous. A spacecraft that could return. The familiar shape was still learning what it could become. In November, Atlantis launched again, Space Transportation System 74, the second shuttle docking mission with Mir. The crew was Kenneth Cameron, James Halsell, Jerry Ross, William MacArthur, and Chris Hadfield. Chris Hadfield became the first Canadian to visit Mir. Atlantis carried a docking module. This module would remain attached to the Russian station. Its purpose was practical. Future shuttle dockings needed sufficient clearance and a suitable arrangement. The solution was to add a new piece to Mir. The shuttle carried the module, then used the robotic arm to position it. The module was connected. Atlantis then docked with Mir through the new arrangement. Think about the sequence. A spacecraft carries a piece of another spacecraft. The piece is removed from the cargo bay, attached, then used as the interface through which the carrying spacecraft connects. The shuttle delivered its own future doorway. The familiar shape was still learning what it could become, and now it was modifying the destination so that future visits would be easier. This is more than connection, it is infrastructure. The first docking had proved that the vehicles could meet. The second helped prepare Mir for repeated meetings. One mission changed the conditions for later missions. Again, the shuttle program was building continuity across flights. The docking module would remain, future orbiters would arrive, they would use the interface left behind. A mission could therefore create a path for another mission. The elegant solution was becoming cumulative, not one perfect flight, a sequence, each mission adding something: experience, hardware, procedures, confidence, questions. The familiar shape was still learning what it could become, and the answer was becoming less about the shuttle alone. The year 1996 began with Endeavour, Space Transportation System 72, January. The crew was Brian Duffy, Brent Jett, Leroy Chiao, Winston Scott, Koichi Wakata, and Daniel Barry. The mission retrieved the Japanese Spaceflyer unit. The free-flying spacecraft had been launched by a Japanese rocket months earlier. Now Endeavour approached it. Koichi Wakata used the robotic arm to capture it. The spacecraft was brought into the cargo bay. A Japanese spacecraft launched by one system was retrieved by an American shuttle with an international crew. Again, connection. Not everything in the cargo bay had begun its journey there. The shuttle could meet hardware from other launch systems. Different machines could participate in one mission separated by months and countries. The mission also deployed and retrieved the Office of Aeronautics and Space Technology Flyer, and astronauts performed spacewalks to test techniques and equipment. The future station remained present in the background. Every handrail, every restraint, every tool, every hour outside, practice for a structure that would eventually require years of assembly. The familiar shape was still learning what it could become. In February, Columbia launched on Space Transportation System 75. The crew was Andrew Allen, Scott Horowitz, Franklin Chang Diaz, Maurizio Celli, Jeffrey Hoffman, Claude Nicollier, and Umberto Guidoni. The mission carried the tethered satellite system again. The earlier attempt in 1992 had not achieved the intended deployment. Now the experiment returned. The satellite was deployed on a long conductive tether. This time, it extended much farther. Then, the tether broke. The satellite moved away. The experiment ended differently than planned, but before the break, valuable data had been collected. Again, the enemy. Novel systems can fail in novel ways, but failure does not always erase all knowledge. An experiment can produce useful results even when the final sequence is not the intended one. The tether itself interacted with Earth's magnetic environment. Electrical current was generated. The experiment demonstrated physical effects at a scale difficult to reproduce on Earth. Then the tether separated. The satellite was lost. The mission continued. The familiar shape was still learning what it could become. And sometimes, the answer was not what anyone had planned. In March of 1996, Atlantis launched on Space Transportation System 76, the third shuttle docking mission with Mir. The crew was Kevin Chilton, Richard Searfoss, Ronald Seeger, Michael Clifford, Linda Godwin, and Shannon Lucid. Shannon Lucid would not return with Atlantis. She would remain aboard Mir. The shuttle was now carrying an American astronaut to begin a long-duration stay on a Russian space station. This was not merely a visit, it was a transfer of home. For months, Mir would be where Lucid lived and worked. Atlantis docked, cargo moved, people moved, supplies moved, experiments moved. The boundary between the spacecraft became busy. A docking port may look like a small circular opening. Operationally, it can become a road, food, water, equipment, samples, personal items, scientific hardware, people, everything that can fit through. The elegant solution was not the docking itself, it was what docking allowed to cross. The familiar shape was still learning what it could become, and now it had become a ferry. Shannon Lucid remained aboard Mir. Atlantis returned to Earth. The shuttle had left one of its crew members behind. Months later, another shuttle would come. This created a new kind of continuity. One mission could begin a human journey, another could end it. The astronaut's story no longer fit inside one shuttle flight. The program had expanded beyond the duration of the orbiter. A person could launch on one spacecraft, live on another, return on a later mission. The boundaries between missions were becoming porous. This is the elegant solution in full. Do not demand that one machine do everything. Build systems that can handwork to one another. A shuttle launches. A station supports a long stay. Another shuttle returns. A robotic arm moves cargo. A docking module creates an interface. A relay satellite carries communications. Ground teams support the entire chain. No single component is the mission. The mission exists between them. The familiar shape was still learning what it could become. And now, perhaps, we can answer the strange question more clearly. How did the same spacecraft idea keep becoming a completely different machine, without ever changing its basic shape? Because its deepest purpose was not hidden in the shape. It was hidden in the connections. Connect a laboratory, and it becomes a research station. Connect a telescope to the robotic arm, and it becomes a repair ship. Connect a planetary probe to an upper stage, and it becomes the first step toward another world. Connect to Mir, and it becomes part of a space station. Connect one mission to another, and it becomes a transportation system. The shuttle was not one machine pretending to be many. It was a machine designed to enter relationships, and every relationship created a new function. The elegant solution was the interface, the cargo bay, the robotic arm, the airlock, the docking system, the payload connections, the communications links, the procedures shared between people, the handoff from one spacecraft to another. The familiar shape was still learning what it could become. But the next part of the story is where these connections begin to cascade. One docking makes the next possible. One long duration stay prepares for another. One servicing mission improves the next. One construction test becomes a real construction task. One module becomes the place where another module attaches. The shuttle is approaching the period when its missions will no longer feel like isolated journeys. They will begin to form a chain, a sequence in which each flight changes the conditions waiting for the next. And once that begins, the spacecraft does not merely carry the mission, it carries the future of the mission after it. The familiar shape was still learning what it could become. Now, let us follow the cascade.